Have you ever paused in the quiet of the late evening, when the world outside your window has finally settled into silence, and wondered about the nature of movement? It is a strange paradox of our existence that while we sit here, perfectly still, resting in the comfort of our homes, we are actually traveling at incomprehensible speeds. If you close your eyes and focus on your breathing, you might almost feel the gentle rotation of the earth beneath you. We are spinning. The ground, the oceans, the atmosphere, and the very chair you are resting on are all carrying you eastward at over 1,000 miles per hour. It is a motion so constant, so smooth, and so ancient that our bodies have evolved to ignore it entirely. We feel stationary, yet we are voyagers on a great carousel that never stops. And it is not just the Earth. Our planet orbits the sun, a great gravitational dance that takes 1 year to complete. The sun itself orbits the center of the Milky Way galaxy, dragging our entire solar system along with it through the vast, dark emptiness of interstellar space. And the galaxy, too, is spinning, a majestic pinwheel of 100 billion stars turning slowly in the cosmic void. Rotation, it seems, is the fundamental language of the universe. From the smallest drifting asteroid to the most massive supercluster of galaxies, everything spins. It is the way the cosmos breathes. It is how stability is found in the darkness. The conservation of angular momentum is the silent law that keeps the universe from collapsing in on itself or flying apart into nothingness. It is a comforting thought, is it not, to know that this circular motion is the rule, the standard, the heartbeat of creation. We understand spinning. We played with spinning tops as children, watching them defy gravity as long as they kept moving. We watch figure skaters pull their arms in to spin faster, a perfect physical demonstration of these universal laws. We see the cycle of day and night, the rhythm of the seasons, the rising and setting of the moon, all born from this simple, elegant act of rotation. It feels intuitive. It feels right. It feels like home. But I want to invite you on a journey tonight, a journey that will take us away from this comfortable, intuitive world of large, spinning objects. I want you to come with me into the hidden depths of reality, to a place so small that the rules of common sense begin to unravel, and the comforting laws we trust begin to whisper in strange riddles. We are going to descend into the heart of the atom. We are going to look for the source of this motion, and there, in the quantum silence, we are going to find a mystery that has kept physicists awake for a century. We are going to talk about the electron and the impossible secret it keeps. Take a deep breath and let your imagination shrink. Imagine we are zooming in on your own hand, resting gently by your side. We pass through the landscape of your skin, a rugged terrain of ridges and valleys. We dive deeper past the complex cities of your cells, watching the machinery of biology work its silent magic. We go smaller still until the biology fades away, and we are left with the building blocks of matter itself, the molecules. And then we go deeper. We enter the vast empty cathedral of the atom. For many of us, the image of the atom is one we learned in school, a picture that is as familiar as a friend. We imagine a dense nucleus at the center, like a tiny sun, and around it, electrons orbiting like little planets, spinning on their axes as they circle the core. This is the Bohr model, or perhaps a variation of it, and it is a beautiful image. It mirrors the solar system. It suggests that the rules of the macrocosm, the planets and stars, are reflected perfectly in the microcosm, the protons and electrons. As above, so below. It is poetic, it is elegant, and it is, unfortunately, completely wrong. When we reach the quantum level, the concept of spinning undergoes a transformation so radical that it challenges the very limits of human language. You see, the electron is not a tiny planet. It is not a miniature ball of matter with a surface and an equator, and a North Pole and a South Pole. In the rigorous mathematical eyes of modern physics, the electron is a point particle. It has no radius, it has no volume, it takes up no space. It is a zero-dimensional speck of existence, a fundamental knot in the fabric of the fields that make up our reality. And here lies the great paradox, the silent conflict that sits at the heart of quantum mechanics. Experiments tell us with absolute precision that the electron has a property we call spin. When we pass electrons through a magnetic field, they deflect. They act exactly like tiny bar magnets. They have what physicists call a magnetic moment. In our classical world, magnetism like this is created by moving electric charges. If you take a charged ball and spin it, you create a magnetic field. So, when early physicists first saw this magnetic behavior in electrons, they naturally assumed the electron was spinning. It made perfect sense. It was the only explanation that fit the logic of the world we know. But now, I want you to hold two contradictory thoughts in your mind and let them gently collide in the silence of your contemplation. Thought number one: the electron acts exactly like a spinning ball of charge. Thought number two: the electron is a point with zero size. If you try to combine these two thoughts using the laws of classical physics, something catastrophic happens to the mathematics. Let us try to do this impossible calculation together, just as a thought experiment in the safety of our imagination. If an electron were a tiny ball with a measurable radius, even a radius as incredibly small as we can measure, and it had the angular momentum that we know it has, we can calculate how fast its surface would need to be moving. To generate that specific amount of spin we observe, the equator of this tiny hypothetical electron ball would have to rotate at a speed that is truly terrifying. It would have to move faster than the speed of light, and not just a little bit faster. It would have to scream across the fabric of space-time at velocities that shatter the ultimate speed limit of the universe. Einstein's theory of relativity tells us that nothing with mass can travel at the speed of light, let alone exceed it. If the surface of the electron were moving this fast, the laws of causality would break down. Time would twist in impossible ways. The structural integrity of physics itself would crumble. So we are left with a profound mystery. The electron cannot be spinning. If it were spinning, it would break the universe. And yet, it possesses spin. It possesses the angular momentum. It possesses the magnetism. It is like finding a smile without a face, or a wave without an ocean. It is a noun without a verb. The electron has the property of spin, but it does not perform the action of spinning. How do we reconcile this? How do we wrap our minds, evolved to understand throwing rocks and harvesting crops, around an entity that defies such basic logic? This is where we must let go of our need for visual pictures. We must surrender the comfort of the little solar system model. We must accept that the universe, in its foundational layers, operates on a logic that is stranger and more beautiful than our intuition can grasp. In the early days of quantum mechanics, this problem confused the greatest minds in history. Wolfgang Pauli, one of the fathers of quantum theory, was deeply skeptical of the idea of electron spin when it was first proposed. He called it observable rotation and dismissed it because he knew mathematically that a mechanical rotation was impossible. He knew that the surface speeds would be superluminal faster than light. It felt like a step backward, a return to classical thinking, in a world that was revealing itself to be quantum. And yet, the data was undeniable. The spectral lines of atoms, the unique barcodes of light that elements emit, showed fine splitting that could only be explained if the electron had this intrinsic magnetic property. The universe was telling us something profound. It was telling us that spin is not necessarily a motion. In our human world, spin is something you do. A top spins, a wheel spins, a dancer spins. If they stop moving, the spin disappears. It is a temporary state of being, requiring energy and action. But for the electron, spin is not something it does. It is something it is. Think about the other properties of an electron. It has mass. It has charge. You do not ask, how does the electron do its mass? Or, how fast does the electron move to create its charge? You simply accept that mass and charge are fundamental labels, intrinsic tags, attached to this particle that define what it is. If you took away the charge, it would no longer be an electron. If you took away the mass, it would be something else entirely. Now, we must gently expand our understanding to include spin in this category. The electron's spin is intrinsic. It is built in. It is as fundamental to the electron's identity as its negative charge. The electron does not start spinning when it is born, and it does not slow down as it gets old. It is born with this angular momentum, fixed and eternal, a permanent part of its existence. It is a quantum number, a label woven into the very fabric of the particle. But why does this feel so unsatisfying to us? Why does a part of your mind perhaps resist this explanation? It is because we are creatures of story and mechanism. We want to look under the hood. We want to see the gears turning. When we are told it just is, it feels like a magician refusing to reveal his trick. We want to know how a point particle, a speck of nothingness, can have a North Pole and a South Pole. We want to know how it can feel a magnetic field if it is not moving. This desire for a mechanical explanation is natural. It is the curiosity that drove our ancestors to understand the seasons and the tides. But the quantum world requires a different kind of curiosity, a curiosity that is willing to sit with the unknown, to float in the sea of paradox without reaching for the shore of easy answers. Imagine, if you will, that we are floating in deep space, far away from any star. It is quiet here. The darkness is absolute. In this void, we see a single electron. It is not a hard little marble. It is a disturbance in the field, a ripple in the silence. And even though it is motionless in the traditional sense, it carries with it a hidden energy, a potential for rotation that never actualizes into physical movement, but remains present as a force. It is like a coiled spring that never releases, holding its tension forever. It is a potentiality that defines how it interacts with every other particle in the universe. This spin is what gives matter its structure. Without this mysterious, impossible property, the electrons in an atom would all collapse into the lowest energy state, crowding together in the center. Chemistry, as we know it, would not exist. The complex bonds that form water, the carbon chains that form life, the very structure of the DNA in your cells, all of it relies on the specific rules of electron spin. The Pauli exclusion principle, which prevents matter from passing through other matter, which allows you to sit on a chair without falling through it, is a direct consequence of this quantum spin. So, in a very real and tangible way, the solidity of the world around you, the feeling of the floor beneath your feet, the touch of a loved one's hand, all of these physical sensations are born from this ghostly, impossible property. We are sustained by a paradox. We are built on a foundation of particles that spin without spinning. that point without dimension, that act without moving. As we lie here in the dark contemplating this, does the universe not seem suddenly more vast? We often think of vastness in terms of distance, billions of light years, endless galaxies. But there is a vastness of complexity, a depth of mystery that exists right here, in the tip of your finger. The electrons dancing in the atoms of your own body are defying the logic of the large-scale world in every passing nanosecond. They are carrying secrets that physics can describe, but not fully explain. The mathematics works. The equations of Paul Dirac, which we will explore later in our journey, describe this behavior with breathtaking accuracy. We can predict the magnetic moment of the electron to 12 decimal places. It is the most precise prediction in the history of science. We know what happens with a certainty that borders on the miraculous, but the why, the intuitive picture of what is actually happening down there in the dark, that remains veiled. It is a reminder of our place in the cosmos. We are middle-sized creatures, evolved to navigate a middle-sized world. We understand rocks and rivers. We understand day and night. But the universe extends far beyond our intuitive grasp, both upwards into the infinite and downwards into the infinitesimal. And perhaps that is where the beauty lies. If we could understand everything, if the universe were merely a complex clockwork machine that we could take apart and explain fully, it might lose some of its magic. But the electron tells us that reality is not a machine. It is something more fluid, more subtle, more profound. It suggests that at the bottom of everything, there is not a gear turning, but a quality of existence that transcends our definitions of motion and stillness. Tonight, we are going to walk the edge of this mystery. We are not going to solve it, for even the greatest Nobel laureates have not solved it in the way you might solve a crossword puzzle. Instead, we are going to appreciate it. We are going to look at the spin of the electron and see it as a koan, a riddle offered by nature to help us expand our minds. We will look at how this discovery was made, trace the footsteps of the confused and brilliant men and women who first stumbled upon it. We will look at how this invisible spin connects the entire universe, linking the magnets on your refrigerator to the fusion reactions in the sun. And we will ask ourselves what it means to exist in a reality where the fundamental building blocks are so wonderfully, beautifully strange. So, let the stillness of the room settle around you. Let the heavy classical world of gravity and friction fade into the background. We are no longer bound by the intuitive rules of the playground. We are entering the quantum realm. It is a place of shadows and probabilities, of things that are and are not at the same time. It is a place where a particle can be here and there, where a cat can be alive and dead, and where a point of nothingness can spin forever without ever moving an inch. This is the story of electron spin. It is a story of how we learned to see the invisible. It is a story of how we were forced to abandon our pictures and trust the math. And ultimately, it is a story about the limits of human imagination and the infinite capacity of the universe to surprise us. As we begin this descent, remember that you are made of these mysteries. You are not an observer looking in from the outside. You are a collection of these spinning paradoxes, organized into a consciousness that can wonder about itself. The mystery is not out there. The mystery is you. Feel the weight of your body on the bed or the chair. That resistance you feel, that solidity that keeps you from sinking through the floor, is the silent voice of electron spin, pushing back, claiming its space in the universe. You are being held up by the quantum laws we are about to explore. You are cradled by the strange physics of the very small. So let us drift. Let us let go of the need to have a picture that makes sense in the way a spinning top makes sense. Let us open our minds to a new kind of motion, a motion that happens in the abstract spaces of mathematics and reality. Let us wonder together why the universe chose to give its smallest children such a peculiar gift. Why must the electron spin? And if it is not spinning in space, where is it spinning? These are the questions that will guide us through the night. The answers may not be simple, but the journey to find them is full of wonder. And in the silence of that wonder, we might just find a different kind of understanding, not the understanding of a mechanic looking at an engine, but the understanding of a traveler looking at a vast, star-filled sea, realizing that the water is deep, and the horizon is far, and the voyage is beautiful. Let us gently drift away from the abstract stillness of your room and travel back through the mists of time, anchoring ourselves in a specific moment of human history. The year is 1922. The location is Frankfurt, Germany. The world is still recovering from the scars of the Great War, and the streets are filled with the noise of reconstruction and the frantic energy of a changing century. But we are seeking a quiet place, a sanctuary of glass and metal, where two men are about to ask the universe a question that will change everything. We find ourselves in a dimly lit laboratory, smelling of ozone and stale tobacco smoke. Here, physicists Otto Stern and Walter Gerlach are building a machine. It is not a large machine, not like the giant particle colliders we have today that span miles beneath the Earth. This is a tabletop experiment, a delicate assembly of pumps, magnets, and furnaces constructed with the patience of watchmakers. They are trying to test the very nature of the atom to see if the strange new theories of the quantum world, the theories that say energy and motion come in discrete packets, are actually true in the physical world. The heart of their experiment is silver. Imagine a small furnace glowing with heat, containing a single nugget of pure silver. As the furnace gets hotter, the silver begins to melt and then to boil. Silver atoms, liberated from their metallic bonds, turn into a vapor. They become a ghostly gas, a breath of metal. Stern and Gerlach allow a thin stream of these silver atoms to escape through a tiny slit, creating a beam. It is a beam of matter, invisible to the naked eye, shooting through the vacuum of their apparatus like a silent arrow. Now, why silver? This choice was not random. It was a poetic stroke of chemical luck. A silver atom has 47 electrons. 46 of them are arranged in closed, symmetrical shells, effectively canceling each other out. They are a quiet audience. But the 47th electron, the lonely valence electron, sits in the outermost shell, orbiting the nucleus alone. Because of this solitude, the magnetic properties of the entire silver atom are determined almost exclusively by this single, lonely voyager. By shooting silver atoms, Stern and Gerlach were, effectively, shooting individual electrons through their machine, wrapped in a heavy coat of silver, to give them momentum. The beam of silver atoms travels through the dark vacuum chamber, but before it hits the glass detector plate at the back, it must pass through a gauntlet. It must pass between the poles of a powerful magnet. But this is not an ordinary magnet. One pole is shaped like a sharp knife edge, and the other has a groove. This asymmetry creates a magnetic field that is stronger on one side than the other. This is crucial. If the silver atoms act like tiny magnets, which we suspected they might, this uneven field will push them. It will exert a force. Here is where our intuition, the intuition of the spinning top and the planet, sets an expectation. If you were to take 1,000 toy tops, spin them, and throw them through the air, Their axes of rotation would be pointing in every possible direction. Some would be pointing straight up, some straight down, some horizontal, and every single angle in between. It would be a chaotic, random distribution. If the electron is just a tiny spinning ball of charge, it should behave the same way. As the atoms fly through the magnet, those with their north poles pointing up should be pushed up. Those pointing down should be pushed down. Those pointing sideways should not be pushed at all. And because the atoms should be spinning at every possible random angle, the result on the glass plate at the back of the machine should be a smear, a continuous vertical line of silver, a fade from top to bottom, representing the infinite variety of angles that a spinning object can have. This is what classical physics predicted: a smear, a blur, a continuous spectrum of possibilities. Nature, we believed, was smooth. It did not make jumps. It did not make abrupt choices. Stern and Gerlach ran the experiment. They let the silver beam flow. They waited as the invisible atoms struck the glass plate, one by one, building up a pattern layer by atomic layer. In the folklore of physics, there is a wonderful detail about what happened next. The silver deposit on the glass was so thin it was invisible. But Otto Stern was a smoker of cheap cigars, which were high in sulfur. As he breathed over the glass plate, the sulfur in his breath reacted with the silver, turning it into jet-black silver sulfide. Slowly, like a photograph developing in a dark room, the message from the quantum universe appeared. It was not a smear. It was not a continuous line. There were two distinct spots. One spot was shifted clearly up. The other spot was shifted clearly down. Between them, where the sideways spinning atoms should have been, there was nothing. The glass was empty. Let the weight of this sink in. It is as if you threw 1,000 coins into the air, and instead of landing in a pile of random orientations, every single coin landed either perfectly heads up or perfectly heads down, with absolutely no coins landing on their sides or at an angle. Or imagine spinning 1,000 tops and finding that they can only spin perfectly vertical or perfectly inverted, with no tilt allowed. The universe had made a binary choice. The electron could be spin up or spin down. There was no in-between. This result, known as the Stern-Gerlach experiment, is one of the most profound revelations in the history of human thought. It shattered the idea of a smooth, continuous reality. It showed us that at the fundamental level, existence is pixelated. It is quantized. The angular momentum of the electron, that property we call spin, is not a continuous dial that can be turned to any setting. It is a switch. Click up, click down. This behavior is what physicists call space quantization. It means that the electron does not just have a set amount of spin, but the direction of that spin is also constrained by the laws of the quantum. When the electron enters the magnetic field, it is forced to align itself. But it does not align like a compass needle, which can swing gently to find north. It snaps into one of two allowed states. It aligns either with the field or against the field. It is an all-or-nothing proposition. But why? Why does nature forbid the angles in between? Why is the electron not allowed to point 45 degrees to the right? It is as if the space around the electron is not a neutral stage, but a structured lattice that only permits certain moves, like a bishop on a chessboard that can only move diagonally. The electron is locked into a relationship with the geometry of the universe that is far more rigid and strange than our open, free-roaming experience of life. This discovery brings us back to the paradox we explored in the beginning. We established that the electron cannot be physically spinning because it would have to move faster than light. Now, we see that its spin behaves in a way that no physical spinning object ever could. A tennis ball can spin at any angle. An electron can only spin in two. This reinforces the uncomfortable truth. Electron spin is not a mechanical rotation. It is an intrinsic form of angular momentum that obeys a completely different set of rules. It is a quantum label. It is a fundamental degree of freedom that has only two settings. Think about the implications of this two-ness. We live in a world of complexity, of shades of gray, of infinite variation. The sunset is not just light or dark. It is 1,000 hues of orange and purple. The temperature is not just hot or cold. It is a sliding scale. But down in the basement of reality, underneath the complexity of the sunset and the weather, the building blocks are making binary choices. Up, down, plus, minus, 1, 0. This binary nature of the electron is actually the foundation of the information age. In a very poetic sense, the computer you are using right now, which processes information in ones and zeros, is mimicking the fundamental binary language of the matter it is made of. The universe is, at its heart, a system of information. The electron carries a bit of information, its spin state. It is the original memory storage, the primordial switch. But the mystery deepens. If the electron is only up or down when we measure it, what is it doing before we measure it? When the silver atom is flying through the vacuum before it hits the magnet, which way is it pointing? This is where the quantum world asks us to abandon our last shreds of classical logic. You might think, well, the electron must be either up or down. We just don't know which one until we look. That would be the sensible answer. That would be the answer that lets us sleep soundly. But the universe is not sensible. Before the measurement, the electron is not up. It is not down. It is in a state of superposition. It is a mixture of both. It is a ghostly combination of upness and downness existing simultaneously. It is not that the electron is hiding its true state from us. It is that the state itself is undefined. The electron exists in a cloud of probability, a haze of potential. It is the act of measurement, the interaction with the magnetic field, that forces the universe to make a decision. The magnet asks the question, are you up or down? And the electron, under the pressure of that interrogation, snaps into one of the two allowed answers. This is the collapse of the wave function, a phrase you may have heard whispered in the corridors of popular science. It is the moment when the hazy dream of the quantum world hardens into the concrete reality of the physical world. The Stern-Gerlach experiment is a machine that turns possibilities into facts. It turns the maybe of the superposition into the yes or no of the silver spot on the glass. Imagine the philosophical weight of this. We tend to think of the future as something that is already written, or at least something that flows smoothly from the present. But at the quantum level, the future is a branching tree of probabilities. Until an event occurs, until a measurement is made, reality is fluid. The electron explores all paths. It spins all ways. It is only when it touches the world, when it interacts, that it commits. There is a beautiful, if slightly melancholic, thought here. We, as massive creatures made of septillions of atoms, are constantly interacting. We are constantly touching the air, the ground, the light. We are constantly measured by the universe. Because of this, our quantum possibilities have long since collapsed. We are fixed in a single reality. We are the result of countless trillions of quantum choices made every microsecond. We are the hardened ash of the quantum fire. But the electron, in its isolation, retains the magic of the undecided. It retains the freedom to be everything at once. As we visualize those two black spots of silver on the glass plate in 1922, we are looking at the footprints of a ghost. We are seeing the shadow of a dimension we cannot enter. Stern and Gerlach did not just discover a property of the electron. They discovered a boundary. They found the edge where our rules end and the rules of the subatomic begin. And yet, despite knowing how it behaves, knowing that it splits into two, knowing that it is quantized, we still have not answered the question, what is it? If it is not a spinning ball, but it has angular momentum and it makes binary choices, what does that look like? To answer this, we have to go even deeper. We have to leave the tangible world of magnets and silver furnaces and enter the realm of pure mathematics. We have to meet a man who was so quiet, so strange, and so brilliant that he was often called the mystic of the atom. His name was Paul Dirac. And he would be the one to find the electron's true face, hidden in an equation that combined the two greatest theories of the 20th century. But before we meet Dirac, I want you to return your focus to the sensation of up and down. In the vast emptiness of space, these words have no meaning. There is no floor in the cosmos. There is no ceiling. Up is just a direction we choose, usually away from the gravity that binds us. But for the electron, up is defined by the magnetic field it feels. Its north is defined by the external force it encounters. This suggests something profound about identity. The electron's spin state, its upness or downness, is not something it possesses entirely on its own. It is defined in relation to the field around it. It is a relationship. In the absence of a field to measure it, the spin is just a potential, a cloud. It takes an environment to define the orientation, just as we are defined by our relationships, by the context of our lives. The electron finds its direction only when it encounters a force larger than itself. So, as we leave the smoke-filled laboratory in Frankfurt, watching the two black spots of silver sulfide dry on the glass, we carry with us a new piece of the puzzle. The universe is granular. It is binary. It forces choices. And the spin of the electron is the mechanism of that choice. It is the fundamental toggle switch of reality. But if the electron is a point, a zero-dimensional speck, how can it have a front or a back? How can a point rotate? How can something with no structure have an orientation? The paradox from the first chapter has not been solved. It has only deepened. We have seen the fingerprints of the suspect, but we still have not seen the suspect's face. The spin is real. The quantization is real. The splitting of the beam is real. But the physical picture is dissolving. We are floating in a sea of abstraction where the only lifeline is the mathematics. In the next chapter, we will grab onto that lifeline. We will see how a simple attempt to merge Einstein's relativity with quantum mechanics produced a magical, unexpected child, the spin. We will see that spin is not a mechanical accident, but a necessary consequence of the way time and space are woven together. For now, rest in the certainty of the two spots, up and down. The universe may be mysterious, but it is not indecisive. It knows its mind. And in the quiet hum of the atoms that make up your body, those decisions are being made over and over again, sustaining the beautiful, stable illusion of the world you know. We have traveled from the spinning earth beneath our feet to the silver atoms flying through a vacuum chamber in Frankfurt. We have seen the paradox of the spinning point and the binary mystery of the up and down spots on the glass. Now, We must leave the physical world behind entirely. We must close the door on the laboratory, with its pumps and magnets and smells of sulfur, and enter a room that is much quieter, yet infinitely more vast. We are entering the silent cathedral of pure mathematics. It is the year 1928. The golden age of physics is in full bloom, but there is a crack in the foundation. Two great theories have risen to explain the universe, like two mighty towers standing on opposite sides of a river. On one side stands quantum mechanics, the theory of the very small. It describes atoms, electrons, and photons with a probabilistic haze, a world of waves and uncertainties governed by the famous equation of Erwin Schrödinger. On the other side stands special relativity, the theory of the very fast. This is Albert Einstein's masterpiece, describing a universe where space and time are woven together into a single fabric, where nothing can travel faster than light, and where mass is just a frozen form of energy. The problem, the source of deep anxiety for the physicists of the time, was that these two theories refused to speak to each other. They were like two languages that shared no common words. Schrödinger's equation, beautiful as it was non-relativistic. It assumed that time ticked forward steadily and universally, just as Isaac Newton had believed centuries before. It worked perfectly for slow-moving electrons, for the quiet hum of chemistry. But if an electron moved fast, and electrons often do, Schrödinger's math fell apart. It could not handle the warping of time. It could not handle the speed of light. It was a theory of the slow, trying to describe a particle that lived for speed. Enter Paul Dirac. If you were to meet Paul Dirac in the courtyards of Cambridge University, you might not notice him. He was a tall, thin man, often silent, possessing a demeanor of such profound reserve that his colleagues created a unit of measurement called the Dirac. One Dirac was defined as the rate of one word per hour. He was not a showman. He was not a philosopher in the public sense. He was a literalist, a man who saw the world with a clarity that was almost unnerving. To him, the beauty of the universe was not in its landscapes or its stars, but in its equations. He believed, with a religious fervor, that the fundamental laws of nature must be mathematically beautiful. If an equation was ugly, he reasoned, it could not be true. Dirac looked at the broken bridge between quantum mechanics and relativity, and he decided to fix it. He did not set out to discover the secret of electron spin. He did not set out to explain the magnets on your refrigerator. He simply wanted consistency. He wanted an equation that would describe the electron moving at any speed, even close to the speed of light, without breaking the rules of Einstein's space-time. He wanted to harmonize the very small with the very fast. He sat alone in his room, staring at the symbols, playing with the algebra of the cosmos. He was looking for the square root of a wave operator, a mathematical puzzle that seemed impossible to solve using ordinary numbers. If you take the square root of 4, you get 2. It is simple. But Dirac was trying to take the square root of a complex differential operator, and ordinary numbers, scalars, simply would not work. They failed. The math resisted, and here, in the silence of his thought, Dirac made a leap of intuition that borders on the artistic. He realized that if ordinary numbers could not solve the puzzle, he needed a different kind of object. He needed a mathematical entity that was richer, more complex. He turned to matrices, grids of numbers that follow their own peculiar rules of multiplication. He found that if he replaced the simple coefficients of his equation with 4x4 matrices, the algebra suddenly unlocked. The pieces clicked into place. The square root was found. The result was the Dirac equation. It is, by many accounts, the most beautiful equation in the history of physics. It is compact, elegant, and seemingly simple, carved onto the tombstone of Dirac himself in Westminster Abbey. But when Dirac wrote it down in 1928, he unleashed a monster. The equation was much smarter than he was. It knew things he did not. When he looked at the solution his equation provided, he found something startled him. Remember that Schrödinger's equation treated the electron as a single wave function, a simple scalar value. But Dirac's equation, because it used those 4x4 matrices, produced a solution that had 4 components. The electron was not just one thing. It was a 4-part entity. What were these 4 parts? Dirac analyzed them carefully. 2 of the components seemed to describe the electron we know. But why 2? Why not 1? As he looked closer, he realized that the math was describing 2 distinct states for the electron, states that differed only by a tiny amount of energy in a magnetic field. One state corresponded to spin up. The other corresponded to spin down. Let us pause and appreciate the magnitude of this moment. Before this, spin was just a band-aid. It was an ad hoc idea glued onto the side of quantum theory because experiments like Stern-Gerlach demanded it. Physicists said, okay, the electron has spin, and they wrote it into their calculations by hand. They forced it in, but Dirac did not put spin into his equation. He did not invite it. He did not even think about it. He simply asked, how does an electron move relativistically? And the equation replied, it spins. Spin was not an accident. It was not a random accessory given to the electron by a whimsical creator. The Dirac equation revealed that spin is a necessary, unavoidable consequence of the marriage between quantum mechanics and relativity. It is the child of the union between the logic of the atom and the geometry of space-time. If you live in a universe that obeys Einstein's rules of space and time, and you are a quantum particle, you must have spin. You have no choice. The math demands it. This is a moment of profound revelation. It tells us that this strange property, this angular momentum that is not a rotation, this binary up-down choice, is woven into the deepest structure of reality. It arises because space and time are mixed. The electron spins because it is a creature of space-time, navigating a 4-dimensional reality that we can barely imagine. So, the paradox we started with, the electron that spins without moving, is resolved not by a mechanical explanation, but by a geometric one. The electron is not a spinning ball. It is an object that carries the imprint of space-time symmetry. Its spin is the way it remembers its orientation in a universe where time and space can twist into each other. It is a label that tells the universe how to handle this particle when it moves through the fabric of relativity. But the Dirac equation was not done with its revelations. I mentioned that the solution had 4 components. 2 of them explained the spin of the electron, up and down. But what about the other 2? For a while, these extra 2 components were a source of embarrassment for Dirac. They seemed to describe a particle that was exactly like an electron, with the same mass and the same spin, but with negative energy. In physics, negative energy sounds like a mistake. It sounds like a ball rolling off the floor and falling into a basement that has no bottom, gaining speed forever. It seemed to imply a universe that was unstable, a reality that should collapse in a flash of light. Many physicists thought the equation was flawed. They told Dirac to ignore those extra parts, to cut them out. But Dirac, the mystic of precision, listened to his math. He trusted the beauty of the structure more than the intuition of his peers. He argued that these negative energy solutions were real. He reinterpreted them. He proposed that if there is a sea of negative energy that is completely full, a hole in that sea would look like a particle with positive energy, but with an opposite electrical charge. If the electron is negative, this new particle would be positive. It would be a mirror image, a doppelganger. 3 years later, in 1931, an experimentalist named Carl Anderson was looking at cosmic rays, particles from deep space, passing through a cloud chamber. He saw a track that curved exactly like an electron, but in the wrong direction. It was positive, not negative. He had found Dirac's ghost. He had found the positron. He had discovered antimatter. Think of the chain of thought here. A man sits in a room in Cambridge, writing symbols on a piece of paper, trying to make two theories agree. Because he insists on mathematical beauty, his equation tells him that the electron must spin. And then, as a bonus, it tells him that for every particle of matter, there must be an equal and opposite particle of antimatter. It predicts the existence of a mirror universe. And he is right. He is right about all of it. This is the power of the human mind when it speaks the language of the cosmos. It bridges the gap between the scratch of a pen on paper and the fundamental architecture of reality. So, what does this mean for us as we drift in the quiet of this contemplation? It means that the spin of the electron, which keeps your atoms from collapsing, which creates the magnetism in the lodestone, is a direct signal from the relativistic nature of the world. It is a whisper from the speed of light. When you look at a magnet sticking to your fridge, you're seeing a relativistic effect magnified to a visible scale. You're seeing the consequences of Einstein's space-time acting in your kitchen. The electrons in that magnet are dancing to the tune of the Dirac equation, aligning their spins, summing their tiny quantum voices into a force that you can feel with your hand. It is strange, is it not? We tend to think of relativity as something that only matters for spaceships or black holes. We think of it as a theory for the out there. But Dirac showed us that relativity is in here. It is inside the carbon atoms of your skin. It is inside the oxygen you breathe. Without the rules of relativity, the electron would not spin. Without spin, the exclusion principle would not work. Without the exclusion principle, matter would collapse. You exist in your solid, stable form because of relativity. You are a child of Einstein and Schrödinger, held together by the glue of Dirac's genius. And yet, even the Dirac equation is not the end of the story. It is a beautiful plateau, a place where the view is magnificent, but there are peaks rising higher still in the distance. The equation treats the electron as a lone traveler moving through a field. But electrons are never truly alone. They are surrounded by a cloud of virtual particles, a buzzing hive of activity that flickers in and out of existence in the vacuum. As physicists looked closer at the electron in the decades following Dirac, they found that his beautiful prediction was slightly off. The magnetic strength of the electron, its G factor, was predicted by Dirac to be exactly 2. Exactly. A perfect integer. But when they measured it with even greater precision, they found it was not 2. It was 2.031 sign. It was a tiny deviation, a whisper of a discrepancy. To some, it might have looked like experimental error, but to the ears of a physicist, it sounded like a drumbeat. It meant that something else was happening. It meant that the electron was interacting with something hidden, something that even Dirac had not seen. The journey into the spin is a journey that goes deeper and deeper into the void. We started with a spinning ball. We found it was a point. We found it was a binary choice. We found it was a relativistic spin-or. And now we see that it is a gateway to the quantum vacuum, to the frothing, boiling sea of virtual particles that makes up what we call empty space. But for tonight, let us rest with Paul Dirac. Let us appreciate the quiet courage of a man who followed the math into the dark and found a universe more symmetrical and more beautiful than anyone had dared to dream. Let us appreciate the elegance of a world where properties like spin are not random accidents, but necessary threads in the tapestry of space-time. Imagine the electrons in your body right now, octillions of them, each one obeying that four-component equation, each one carrying the secret of the positron, each one spinning because the geometry of the universe demands it. You are a symphony of relativistic quantum mechanics. You are a masterpiece of math. As you breathe in and out, feeling the stillness of the night, remember that this stillness is an illusion. Deep down, in the basement of your being, there is a frantic, precise, and beautiful dance of numbers and fields. You are vibrant. You are electric. You are spun from the fabric of space-time itself. And as we prepare to leave the era of Dirac, we must ask, what is that tiny deviation? What is that 0.2319? It seems so small, like a grain of sand on a mountain. But in physics, the smallest keys often open the largest doors. That tiny anomaly is going to lead us to the most successful theory in the history of science. It is going to lead us to quantum electrodynamics. It is going to show us that the empty space around the electron is not empty at all, but alive with ghosts. So, let the beauty of the Dirac equation settle in your mind like a calming mantra. The universe is logical. It is ordered. It flows from simple principles into complex forms. And you are one of those forms, a conscious observer made of spinning stardust, capable of understanding the equation that describes you. Rest in that knowledge. Rest in the elegance of the design. The spin is the anchor. The math is the map. And the journey is far from over. Let us settle back into the rhythm of the night. The silence of the room around you is heavy and comforting, a blank canvas upon which we can paint the invisible structures of the universe. We left our last contemplation hanging on a number. It was a small number, a tiny fraction, a delicate splinter in the perfect geometric wood of Paul Dirac's equation. Dirac, with his love for mathematical purity, predicted that the magnetic strength of the electron, the G factor, should be exactly 2, not 2.1, not 1.9, 2. It was an integer. It was whole. It was beautiful. But the universe, in its infinite complexity, whispered a correction. When the experimentalists looked closer, squinting through their instruments, at the behavior of electrons in magnetic fields, they found that the number was not 2. It was 2.002319304361, and so on. To the unquiet mind, this might seem like a triviality. Who cares about the third or fourth decimal place? In the rush of our daily lives, where we round up hours and approximate distances, such precision feels obsessive. But in the cathedral of physics, a deviation in the fourth decimal place is not a detail. It is a scream. It is a crack in the wall of the temple. It tells us that the theory, no matter how elegant, is missing something vital. It tells us that there is a ghost in the machine. Tonight, we are going to follow that ghost. We are going to slip through that tiny decimal crack and find ourselves in a world even stranger than the relativistic spin of Paul Dirac. We are going to discover that empty space is an illusion and that solitude is impossible. We are going to learn that the electron spins not in a vacuum, but in a roiling, boiling ocean of hidden light. To understand this, we must travel to the summer of 1947. The world was waking up from the nightmare of the Second World War. The atomic bomb had been dropped, revealing the terrifying power of the nucleus, and physicists were now the celebrities and the feared wizards of the new age. In June of that year, a group of the greatest minds on the planet gathered at a small inn on Shelter Island, off the tip of Long Island in New York. Imagine the scene: the smell of salt water and pine trees, the sound of waves lapping against the shore, and there, sitting in a conference room, were giants: Robert Oppenheimer, the father of the bomb; Hans Bethe, the man who figured out how stars shine; and a young, brash genius named Richard Feynman, who saw the world in a way no one else did. They were there because physics was stuck. The beautiful equation of Dirac, which we admired so much in the last chapter, had hit a wall. When physicists tried to use it to calculate how an electron interacts with light, how it absorbs and emits photons, the math broke. It did not just give the wrong answer. It gave the answer of infinity. Every time they tried to calculate the mass of the electron or its charge with high precision, the equations spiraled out of control, spitting out nonsense. It was called the ultraviolet catastrophe of quantum electrodynamics. The theory was useless for anything beyond the simplest approximations. Into this atmosphere of frustration walked two experimentalists, Willis Lamb and Polycarp Cush. They did not bring theories. They brought data. They brought the Lamb shift and that stubborn, precise measurement of the electron's magnetic moment. They showed the room that the electron was definitely, absolutely, undeniably wobbling more than Dirac said it should. The anomaly was real. The theory had to change. The breakthrough that followed is one of the greatest intellectual achievements of our species. It required a new way of seeing nothingness. Let us conduct a thought experiment. Imagine you are looking at a perfectly calm ocean. From a high altitude, the surface looks like a sheet of blue glass. It is flat. It is empty. It is silent. This is the classical view of a vacuum. It is a void where nothing exists. But if you were to zoom in, to lower your altitude until you were hovering just inches above the water, you would see that the calm is a lie. The surface is alive with tiny ripples, frothing bubbles, and momentary sprays of mist that jump up and fall back down in the blink of an eye. The quantum vacuum is exactly like this ocean. Heisenberg's uncertainty principle, which tells us we cannot know the position and momentum of a particle at the same time, also applies to energy and time. It says that for very, very short periods of time, the amount of energy in a space can fluctuate wildly. You can borrow energy from the bank of the universe as long as you pay it back almost instantly. What does this borrowed energy do? It manifests as matter. In the empty space right in front of your nose, and in the empty space between the stars, pairs of particles are constantly popping into existence. An electron and its antimatter twin, a positron, emerge from nothing, loop around each other, and then collide and annihilate back into nothingness. They live for a fraction of a nanosecond. They are ghosts. Physicists call them virtual particles. This sounds like science fiction, or perhaps a fever dream. But it is the bedrock of modern physics. Space is not a stage. It is an active participant. It is a seething foam of potentiality. Now, place our lonely electron into this foam. According to Dirac, the electron was a solitary actor moving through a quiet void. But now we know the void is a crowded room. As the electron moves, it is constantly disturbing the sea of virtual particles around it. It pushes against the virtual electrons. It attracts the virtual positrons. It emits virtual photons, packets of light, and then reabsorbs them before anyone can see. Think of a celebrity trying to walk through a dense crowd. They cannot move freely. They are slowed down. They are surrounded by a sphere of influence, a cluster of fans and photographers that moves with them. The celebrity and the crowd become a single, complex object. You cannot interact with the celebrity without interacting with the crowd first. This is what happens to the electron. It becomes dressed by the vacuum. The bare electron, the theoretical point particle of Dirac, is forever hidden from us. What we see, what we measure, and what spins in our magnetic fields is the electron plus its cloud of virtual particles. It is the electron cloaked in a swarm of ghost light. This cloud changes the physics. When the electron spins, it is not just the simple rotation of a point. It is the complex churning motion of this entire cloud. The virtual photons that the electron tosses back and forth create a kind of drag, a subtle resistance, a tiny shift in the center of gravity of the particle. This is the source of the anomaly. This is the origin of the 0.023. That extra bit of magnetic strength comes from the cloud. The electron feels the magnetic field, not just directly, but also through the filter of this virtual entourage. The G factor is not 2 because the electron is not simple. It is a fuzzy, vibrating mess of interactions. The theory that describes this beautiful mess is called quantum electrodynamics, or QED. It was forged in the years after Shelter Island by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga. They found a way to tame the infinities. They found a way to calculate the effect of the cloud. Richard Feynman, in particular, gave us a visual language for this. He drew little diagrams, lines for electrons, squiggles for photons, that turned the impossible algebra into pictures. A straight line is an electron moving. A squiggle is a photon being emitted. A loop in the line is the electron playing catch with itself, throwing a photon into the future and catching it a moment later. These Feynman diagrams allowed physicists to calculate the magnetic moment of the electron with terrifying precision. They calculated the effect of one virtual photon loop, then 2 loops, then 3. Each loop added a tiny correction, a smaller decimal place. Today, the prediction of QED matches the experimental measurement of the electron spin to more than 12 decimal places. It is like measuring the distance from New York to Los Angeles to within the width of a single human hair. It is the most precise theory in the history of science. It is the crown jewel of human knowledge. But let us step back from the triumph of the numbers and return to the feeling of the concept. What does this tell us about the nature of reality? It tells us that isolation is a myth. In the classical world, we think of objects as distinct. Here is a cup. There is a table. Here is a planet. There is a star. We think of ourselves as separate individuals, cut off from the world by the boundary of our skin. But at the level of the electron, this boundary dissolves. The electron does not end where its mass ends. It extends outward, merging with the vacuum, trading energy with the universe, entangled in a constant conversation with the nothingness around it. To define an electron, you must include the entire universe it interacts with. The spin of the electron, then, is not just a property of a particle. It is a property of a relationship. It is the echo of a particle singing to the vacuum, and the vacuum singing back. The wobble that Lamb and Cush measured is the physical evidence of this conversation. It is the signature of the connection between the one and the all. As you lie here, feel the space around you. It looks empty, it looks dark, but you now know that it is filled with a shimmering, invisible light. The air in your room is teeming with virtual particles, appearing and disappearing in a silence deeper than sound. And the atoms of your body, the billions of electrons spinning in your cells, are interacting with this field right now. You are chemically and physically connected to the vacuum. You are dressed in the fabric of the universe. There is a profound comfort in this. We are never truly alone. Even in the deepest void of intergalactic space, an electron carries its cloud with it. It carries a little piece of the universe's complexity wherever it goes. It is home wherever it is, because it is woven into the field that permeates everything. The precision of the number 2.0023 is a testament to this connection. It proves that we can understand the ghost. It proves that the human mind can reach into the invisible, visualize the phantom particles that live for a billionth of a nanosecond, and calculate their effect on the reality we touch. This leads us to a new question, a question that Richard Feynman loved to ask. If the electron is interacting with light, and light is the carrier of the electromagnetic force, then what is the force itself? How do two electrons feel each other? How does a magnet know to push another magnet away? We have talked about the electron spinning. We have talked about it interacting with itself. But the universe is built on interactions between different things. The dance is not a solo. It is a ballroom. In the next chapter, we will watch two electrons meet. We will visualize the exchange that happens between them. We will see that force is not a magical action at a distance, but a physical game of catch. We will see particles throwing photons back and forth like messages, creating the pushes and pulls that build the galaxies and the molecules of your body. We are moving from the anatomy of a ghost to the sociology of ghosts. We are going to see how the spin of one particle talks to the spin of another. We are going to explore the social life of the electron. But for now, stay with the image of the cloud. Visualize the electron not as a hard, lonely point, but as a glowing center of a storm of light that never rests, a storm that is constantly borrowing from the void and paying it back, a storm that makes you, and the chair you sit on, and the earth you spin on, possible. The anomaly is not a mistake. The deviation is not an error. The dirt in the math is the proof of life. The perfect integer 2 belongs to a dead, static universe. The messy decimal belongs to our universe, a universe of flux, of change, of breath, and of light. Rest in the imperfection. Rest in the wobble. It is the wobble of life. We have spent the last movements of our journey looking inward, focusing on the solitary electron wrapped in its shimmering cloak of virtual particles. We have seen how it dances with the vacuum, borrowing and returning energy in a private, eternal cycle of renewal. But the universe is not a collection of solitudes. It is a tapestry of connections. It is a crowded room where every motion triggers a response, and every silence is eventually broken by a whisper. Tonight, we are going to look at how these ghosts speak to one another. We are going to explore the sociology of the subatomic world. Imagine, for a moment, that we are watching two electrons moving through the deep emptiness of space. They are approaching each other. They are identical twins, both negatively charged, both spinning with that peculiar half-integer rhythm, both surrounded by their frantic clouds of virtual light. As they get closer, they begin to slow down. Their paths curve. They push against one another, turning away before they can ever collide. They scatter, flying off into the dark in new directions. In the classical world of Isaac Newton, we would say that there is a force field between them. We would say that the electric field of one pushes against the electric field of the other, acting across the distance like an invisible hand. It is a comfortable explanation, but it is also a magical one. It implies action at a distance, a concept that Newton himself found deeply unsettling. How does one electron know the other is there? How does the information travel across the gap? Does the universe possess some kind of telepathy? Richard Feynman and the architects of quantum electrodynamics gave us a different, more tangible answer. They told us that there is no such thing as a silent field. There is only an exchange of particles. The force that we feel, the push that keeps the electrons apart, is actually a game of catch. Visualize two ice skaters standing on a perfectly smooth, frictionless, frozen lake. They are facing each other. Now, imagine that one skater throws a heavy medicine ball to the other. To throw the ball, the first skater must exert force, and in doing so, they recoil backwards. They slide away. The second skater catches the heavy ball, and the impact of the catch pushes them backwards as well. They drift apart. From a distance, if you could not see the ball, if the ball were invisible, it would look like magic. It would look like a repulsive force had suddenly appeared between the two skaters, driving them away from each other without them ever touching. In the quantum world, the electrons are the skaters, and the ball is a photon. This is the secret mechanism of the electromagnetic force. When two electrons approach each other, they do not telepathically sense a field. Instead, they exchange a virtual photon. One electron shudders and emits a particle of light. This photon travels across the gap, at the speed of light, of course, and is absorbed by the other electron. The momentum of this exchange pushes them apart. The repulsion is a recoil. The force is a bombardment. This changes our entire perception of reality. It means that the universe is not held together by static fields, but by a constant, frantic conversation. Every force you have ever felt is a message being sent and received. When you press your hand against a wall and feel it stop you, you are not touching the wall in the way you think. The electrons in your hand and the electrons in the wall are screaming at each other, trading quintillions of virtual photons every second, shouting, "Move back." No, you move back. The sensation of solidity, of touch, is actually the sensation of a light-speed argument. But these messenger photons are strange. They are not like the photons that stream from the sun to warm your face. Those solar photons are real. They can travel for billions of years across the galaxy, carrying energy from a star to your retina. They are free. The photons exchanged between electrons are virtual. They are prisoners of the interaction. They exist only for the briefest instant, borrowing their existence from the uncertainty principle, crossing the gap and then vanishing as they are absorbed. They are private messages. They cannot be seen by an outside observer. If you tried to intercept one of these virtual photons to look at it, you would change the interaction. You would become part of the system. They are the secret whispers of the cosmos, audible only to the particles involved in the dance. And yet, this exchange is governed by strict rules. The electron cannot just throw photons whenever it wants. There is a probability, a likelihood, a rhythm to the game. This probability is governed by one of the most mysterious numbers in all of science, the fine structure constant. Written as a fraction, it is approximately 1 over 137. 1 over 137. Memorize this number. It is the code for the strength of the electromagnetic interaction. It dictates how tightly electrons hold onto atoms, how easily they emit light, and how strong the repulsion is between them. It is a dimensionless number, meaning it has no units. It is not meters or seconds or kilograms. It is pure number. It is a ratio that seems to be baked into the very operating system of the universe. Physicists have spent decades staring at 137, wondering why the universe chose it. Why not 100? Why not 200? If the number were slightly different, the universe would be unrecognizable. If the interaction were stronger, atoms would be smaller, stars would burn out faster, and life might never have evolved. If it were weaker, matter might not hold together at all. We exist in the Goldilocks zone of this number, a universe tuned for complexity by this mysterious constant. Wolfgang Pauli, the physicist we will meet properly in the next chapter, was obsessed with this number. He spent his life trying to derive it, to find the deeper mathematical reason for its existence. He never found it. It is said that when he was dying in the hospital, in room number 137, he pondered the irony until the very end. The number remains a sphinx, guarding the entrance to a deeper understanding we have not yet reached. But let us return to our two electrons and their game of catch. We have explained repulsion. The throwing of the ball pushes them apart. But what about attraction? How does an electron orbit a proton? How does the negative love the positive? This is where the analogy of the ice skaters becomes difficult. If you throw a ball at someone, it pushes them away. How can you throw a ball at someone and pull them closer? In the quantum world, the rules of momentum and position are fluid. The mathematics of the exchange allows for a negative momentum transfer in certain conditions, depending on the nature of the particles involved. It is as if the skaters were throwing boomerangs, or facing backwards, or exchanging the idea of momentum rather than the object itself. The virtual photon carries the command, "Come closer," just as easily as it carries the command, "Go away." It is the polarity of the charge, the spin, and the phase of the wave function that determines the message. The electron, spinning in its cloud, sends out a call. If it hits another electron, the call is retreat. If it hits a proton, the call is approach. The photon is the carrier, but the charge is the language. This brings us to a profound realization about the empty space in an atom. We are taught that the atom is mostly empty space, a tiny nucleus surrounded by distant electrons. And in terms of mass, that is true. But in terms of activity, the space between the nucleus and the electron is not empty. It is a storm of photons. The electron is tethered to the nucleus, not by a rigid rod, but by a blinding blizzard of virtual light. The atom is held together by its own internal radiation. Every molecule in your body is a web of these exchanges. The carbon atoms bonding to the oxygen atoms in your lungs are held there by the electromagnetic force. That means your breath, your heartbeat, the structure of your DNA are all sustained by the constant emission and absorption of virtual light. You are a being of light, quite literally. You are a construct of photon exchange fields, stabilized by the number 137. Now, pause and let the silence of the room embrace you again. Think about the vastness of this process. It is happening in every star, where the pressure of light keeps the sun from collapsing. It is happening in the darkness of interstellar clouds, where dust grains stick together to form the seeds of new worlds. It is happening in the neural pathways of your brain as you process these words. But there is a catch. There is always a catch in the quantum world. We have explained how electrons interact. We have explained how they push and pull. We have explained their spin and their magnetic moments. But we have not explained their structure. If electrons are attracted to protons, why don't they just crash into the nucleus? Why does the atom have volume? Why does matter take up space? Gravity pulls everything inward. The electrical attraction between the negative electron and the positive nucleus pulls everything inward. By all rights, the universe should be a tiny, dense soup of collapsed matter. You should not be 6 feet tall. You should be a microscopic speck of density. What keeps the atom puffed up? What gives the world its size? What prevents the electrons from all falling into the lowest energy state, piling on top of each other like tired dancers collapsing on the floor? The force of photon exchange explains the movement, but it does not explain the architecture. There must be another rule. There must be a law that says, you cannot sit here. This seat is taken. This brings us to the most distinct and important feature of the electron's social life. Electrons are not just messengers. They are staunch individualists. They refuse to share. They are the ultimate introverts of the cosmos. While particles of light, photons, love to clump together, which is why we can have lasers, beams of coherent light, where billions of photons march in step. Particles of matter, electrons, hate to be in the same state. They demand uniqueness. This demand is what gives the universe its variety. If electrons were like photons, every atom would collapse. Chemistry would be impossible. There would be no periodic table, no valence shells, no bonding, no life. The universe would be a boring, homogeneous blob of energy. The rule that prevents this catastrophe is called the Pauli exclusion principle, and it is intimately, deeply connected to the property of spin. Remember the Stern-Gerlach experiment? Up and down, the binary choice. It turns out that this binary nature is the key to the seating arrangement of the universe. The spin is the ticket that assigns the electron its place in the choir. As we prepare to transition to the next stage of our journey, think of the electron not just as a spinning point, or a dressed cloud, or a photon thrower. Think of it as a particle with a profound sense of personal space. It pushes back against the world, not just with force, but with a fundamental refusal to overlap. This refusal is what you actually feel when you touch a table. It is not just the electromagnetic repulsion. It is the exclusion principle. The electrons in the table are saying, I am already in this quantum state. You cannot be here. You must stay away. The solidity of the world is a consequence of the electron's need for solitude. In the next chapter, we will meet the man who discovered this rule. Wolfgang Pauli was a brilliant, sharp-tongued critic of physics, a man whose intellect was so terrifying that colleagues were afraid to show him their unfinished work. He was the conscience of the quantum revolution, and he discovered that the spin of the electron is not just a label, it is the law. We will see how spin divides the universe into two great families, the fermions, the solitary builders of matter, and the bosons, the gregarious carriers of force. We will see how this division is the yin and yang of existence. But for tonight, stay with the image of the exchange. Visualize the universe as a vast web of conversation. Nothing is untouched. Nothing is ignored. Every electron in the cosmos is aware of its neighbors, constantly testing the boundaries, constantly sending out its little pulses of virtual light, navigating the darkness by the echoes it receives. We are weaving a picture of a universe that is dynamic, interconnected, and vibrantly alive with hidden motion. The silence you hear is not empty. It is the held breath of a cosmos that is busy talking to itself in the language of light and spin. Rest in the knowledge that you are held together by this light. You are a stable form in a rushing river of energy. And the spin is the rudder that keeps you steady in the flow. We have arrived at a pivotal moment in our contemplative journey through the architecture of reality. We have visualized the electron as a ghost, a point, a cloud, and a messenger. We have seen how it dances with light and how it whispers across the vacuum. But there is a question that still hangs in the silence of the room, a question so fundamental that we often forget to ask it. Why is the world solid? Why does your hand not pass through the table? Why does the floor support the weight of the chair? Why do atoms, which are 99.9 repeating percent empty space, act like hard little bricks? If the electron is a cloud of probability and the nucleus is a tiny speck far away, why don't they just slide through each other like ghosts passing in the night? The answer, as we hinted before, lies in the peculiar rules of electron spin. It lies in a law so rigid and so absolute that it creates the very concept of volume in the universe. To understand this law, we must meet the man who discovered it. His name was Wolfgang Pauli. In the pantheon of 20th century physics, Pauli holds a unique place. He was not the dreamer that Einstein was, nor the quiet mystic that Dirac was. Pauli was the critic. He was the sharp, cynical conscience of the quantum revolution. He was a man who famously dismissed a bad scientific paper by saying, "It is not even wrong." He demanded precision. He demanded logic. And in the early 1920s, he was deeply troubled by the chaos of the atom. At that time, the structure of the atom was a puzzle. We knew that electrons orbited the nucleus, but we did not understand how they were arranged. Why did they sit in specific shells? Why didn't they all crash down into the lowest, closest orbit to the nucleus, like marbles rolling to the bottom of a bowl? If gravity or simple electrical attraction were the only rules, every electron in an atom of lead or gold should pile up in the center, creating a tiny, super-dense speck of matter. But they don't. They stack. They arrange themselves in layers, building outwards, creating big, fluffy atoms that can bond and react. Pauli realized that there must be a rule forbidding them from crowding. In 1925, he formulated what we now call the Pauli exclusion principle. It is a simple statement with profound consequences. No two identical fermions may occupy the same quantum state simultaneously. Let us unpack this sentence, for it is the bedrock of your existence. What is a quantum state? Think of it as an address. It is a unique combination of numbers that defines where a particle is and what it is doing. It includes the energy level, the shape of the orbit, and, crucially, the spin. And what is a fermion? This is where the spin becomes the defining character trait of the universe. The cosmos is divided into two great families of particles. It is the deepest division in nature, more fundamental than the difference between plants and animals, or solids and gases. The two families are the fermions and the bosons. The fermions are the particles of matter. They are the electrons, the protons, the neutrons, and the quarks. They are the stuff you are made of. And their defining feature is that they possess half-integer spin. Their spin is 1/2, 3/2, 5/2, and so on. The bosons are the particles of force. They are the photons of light, the gluons that hold the nucleus together, and the Higgs boson. They are the glue of the universe, and their defining feature is that they possess integer spin. Their spin is 0, 1, 2, and so on. This difference in number, 1/2 versus 1, seems trivial mathematically, but in the physical world, it changes everything. It determines the social behavior of the particle. Fermions, the half-integer spinners, are the ultimate individualists. They are the introverts of the cosmos. Because of the exclusion principle, they absolutely refuse to be in the same state as another fermion. If one electron is spinning up in the lowest energy shell of an atom, another electron can join it only if it spins down. Now the shell is full. The address is occupied. If a third electron tries to enter, it is rejected. It must go to a higher energy level, a shell further out. This is why matter has volume. This is why atoms have size. The electrons are forced to stack on top of each other, pushing the boundary of the atom outwards, creating a structure that takes up space. It is the spin, that specific half-integer property, that acts as the barrier. It is the spin that says, stop. This space is mine. Now, contrast this with the bosons, the integer spinners. Bosons are the extroverts. They love to be together. The exclusion principle does not apply to them. You can pack 1 trillion photons into the exact same quantum state, and they will happily coexist. In fact, they prefer it. This is why we can have lasers, streams of coherent light, where every photon marches in perfect lockstep with its neighbors. A laser beam is a party of bosons. A rock is a fortress of fermions. Imagine if you tried to walk through a wall. The atoms in your body are made of fermions, electrons and protons. The atoms in the wall are made of fermions. As your hand approaches the wall, the electron clouds of your atoms begin to overlap with the electron clouds of the wall. Suddenly, the exclusion principle screams a warning. The electrons in the wall are already in their states. Your electrons cannot occupy those states. There is no room at the inn. The resistance you feel, the solidity of the wall, is not just the electrical repulsion we discussed earlier. It is a fundamental degeneracy pressure. It is the universe protecting the individuality of its matter particles. It is the spin of the electron fighting for its right to exist in its own space. Pause and feel the weight of your body on the chair again. We spoke of this sensation in the first chapter, but now we understand it at a deeper level. You are hovering. You are floating on a cushion of quantum exclusion. The fermions in your pants and the fermions in the chair are refusing to merge. You are supported by the stubbornness of half-integer spin. This principle extends far beyond the comfort of your room. It determines the fate of stars. Consider a white dwarf star, the corpse of a sun like ours. When a star dies and stops burning fuel, gravity tries to crush it into nothingness. But as it collapses, the electrons are squeezed closer and closer together. Eventually, they are packed so tightly that all the available quantum states are full. They cannot get any closer without violating Pauli's rule. At this point, the electron degeneracy pressure kicks in. The electrons push back against the crushing weight of gravity, not with heat, not with explosion, but with the sheer quantum refusal to occupy the same space. This pressure can hold up the mass of an entire sun, stopping the collapse and creating a stable, dense, white dwarf. That star is a monument to the power of the exclusion principle. It is a star held up by spin. But why? Why does nature make this distinction? Why does half-integer spin make a particle antisocial while integer spin makes it social? The answer lies in the deep mathematics of how particles behave when you swap them. Imagine you have two identical electrons, electron A and electron B. Because they are identical, if you swap their positions, the universe should look exactly the same. The probability of finding them should not change. However, in the strange arithmetic of quantum mechanics, there is a hidden twist. When you swap two fermions, half-integer spin, the mathematical wave function that describes them flips its sign. It goes from positive to negative. It acquires a minus sign. If you try to put them in the same place, this minus sign leads to a cancellation. The wave function vanishes, zero probability. They cannot be there. But when you swap two bosons, integer spin, the wave function stays the same. No minus sign, no cancellation. They can pile up as much as they want. This connection between spin and statistics, the spin statistics theorem, is one of the most rigorous proofs in theoretical physics. It tells us that the rotation of a particle is inextricably linked to its identity as matter or force. Think about the poetry of this. The universe needs both. It needs the stubborn fermions to build structures, to make protons, atoms, cells, planets, and people. Structures require boundaries. They require distinctness. If electrons were bosons, you would collapse into a microscopic puddle of light. You could not exist as a coherent being. But the universe also needs the friendly bosons to connect those structures. It needs the photons to carry the electromagnetic force between the atoms, binding them together. It needs the gluons to glue the quarks. Force requires flow. It requires superposition. You are a collaboration between these two families. You are a castle of fermions held together by a mortar of bosons. You are built of stubbornness and bound by connection. And the label that decides which role a particle plays is its spin. As we contemplate this, the world feels incredibly orderly. The chaos of the quantum cloud is tamed by the seating chart of Pauli. Every electron has its place. Every proton has its shell. The periodic table of elements, with its columns and rows, is just a map of these quantum states, filling up one by one, governed by the exclusion principle. The chemistry of carbon, the life-giving element, is dictated by the fact that it has 4 vacancies in its outer shell, waiting to be filled. Life itself is a game of finding open seats in the quantum theater. But let us push the mystery a little further. We have said that spin is the label. But what is spin really? We know it is angular momentum. We know it interacts with magnetic fields. We know it determines whether a particle is a fermion or a boson. But we still have that nagging question from the start. It is not spinning like a top. There is a way to visualize the weirdness of half-integer spin that involves the geometry of the universe itself. If you take a normal object, like a book or a cup, and you rotate it 360 degrees, one full circle, it returns to its original state. It looks the same. This is integer spin behavior. But an electron with spin 1/2 is different. If you rotate an electron 360 degrees, it does not return to its original state. In the mathematics of the wave function, it comes back with a minus sign. It is inverted. To get the electron back to exactly where it started, you have to rotate it 720 degrees. You have to turn it around twice. Imagine walking through a room. You turn around a full circle. In our normal world, you face the same wall. But in the electron's world, after one full turn, you would feel different, upside down. You would have to turn a full circle again to truly be back to normal. This implies that the electron is plugged in to the universe in a way that is more twisted, more complex than a simple object. It feels the fabric of space-time in a deeper way. It is connected to the structure of reality by a tether that twists and tangles. This double rotation property is characteristic of spinors, the mathematical objects Dirac used. It hints that the electron sees a larger universe than we do. It navigates a geometry where a circle is not enough to return home tonight as you rest in the dark. Think about that double turn. Think about the hidden depth of the space you occupy. You are made of particles that need 2 full revolutions to find their center. You are made of matter that creates its own space by refusing to share. Wolfgang Pauli, with his sharp eyes and critical mind, saw this truth. He saw that the stability of the world depends on a refusal. The no of the electron is the yes of existence. Without that refusal, there would be no structure. There would be no stars to shine and no eyes to see them. The silence of your room is not empty space. It is a packed auditorium of quantum states, filled to the brim with fermions, organized by the strict rules of the exclusion principle. The air molecules bouncing against your skin are obeying the traffic laws of spin. The photons streaming from a streetlight outside are ignoring those laws, passing through each other like ghosts, carrying the image of the night to your window. We are witnessing the grand dance of the 2 families, the loners and the lovers, the builders and the messengers, the half-integers and the integers, and you, the conscious observer, are the result of their interplay. You are the stillness that emerges from their motion. You are the unity that emerges from their separation. As we prepare to move to the next chapter, we must ask, is this the bottom? Is spin just a label, or is it a sign of something even deeper? We have looked at the electron as a point, but what if it isn't a point? What if the spin is actually the vibration of something much, much smaller? In the next part of our journey, we will dare to ask the question that modern physics is still struggling to answer. We will look at string theory. We will look at the idea that the electron is a tiny vibrating loop of energy playing a note on a cosmic cello. And we will see that spin might just be the music of the universe. But for now, give thanks to the fermions. Give thanks to the stubborn, antisocial electrons that hold their ground. Because of them, you are here. Because of them, the ground is here. Because of them, the universe has a shape. Rest in the solidity of the spin. Rest in the certainty of the exclusion. We have traveled far in our night journey, descending from the spinning earth to the spinning atom, and finally to the stubborn, solitary electron, refusing to share its space. We have accepted the electron as a point, a mathematical speck of 0 dimensions endowed with mass, charge, and this mysterious property we call spin. But there is a restlessness in the soul of physics, a quiet whisper that suggests we are not yet at the bottom. If you look at a point, a true mathematical point, it has no size. If it has mass but no size, its density is infinite. If it has charge but no size, the electrical energy at its center is infinite. Infinities are the nightmares of physicists. They are the places where the equations scream and break. For decades, we swept these infinities under the rug, using clever mathematical tricks to cancel them out, to pretend they weren't there. But what if the problem isn't the math? What if the problem is our picture? What if the electron is not a point at all? Tonight, I want you to close your eyes and let the image of the hard, tiny marble dissolve. Let it melt away. In its place, I want you to imagine something softer, something more elegant, something that hums. Imagine a tiny, shimmering filament of energy, a loop, a string. We are entering the realm of string theory, perhaps the most beautiful and controversial idea in the history of science. It asks us to believe that the fundamental building blocks of the universe are not dots, but notes. It asks us to view reality not as a collection of billiard balls, but as a cosmic symphony. In this view, the electron is a tiny closed loop of string vibrating at a specific frequency. It is like a rubber band floating in the void, jittering and oscillating. But this is not an ordinary rubber band. It is made of pure energy, held together by tension so immense it defies comprehension. And it is incredibly small, 100 billion times smaller than the nucleus of an atom. If an atom were the size of the solar system, a string would be the size of a tree. Now, think about a guitar. When you pluck a guitar string, it vibrates. The way it vibrates, the frequency, the pattern of the wave, determines the sound you hear. If you pluck it one way, you get an A. If you pluck it another, you get a C. The string is the same, but the identity of the sound changes based on the vibration. String theory says the universe works exactly the same way. There is only one kind of ingredient, the string, but depending on how that string vibrates, it manifests to us as different particles. If it vibrates with one pattern, we see an electron. If it vibrates with another, we see a quark. If it vibrates with a third, we see a photon. This is a breathtaking shift in perspective. It means that the difference between matter and force, between the solid electron and the ghostly photon, is just a difference in pitch. It means that you and the chair and the light, reading these words, are all made of the same fundamental stuff, just playing different songs. And what about spin? In the world of point particles, spin was a label we stuck on the electron. It was a brute fact. This has spin 1/2. Why? Because it does. But in the world of strings, spin becomes a consequence of geometry and motion. Imagine the loop of string vibrating, but as it vibrates, it can also rotate. It can twist. The spin of the particle is determined by the vibrational mode of the string combined with its rotation through space. It is a dynamic property. The electron has spin 1/2 because the string that creates the electron is vibrating in a pattern that possesses that specific amount of angular momentum. Suddenly, the koan of the spinning point dissolves. We no longer have to ask how a zero-dimensional object rotates. A string can rotate. A string can sweep out space. The spin is simply the energy of that rotation encoded in the fabric of the particle itself. It is the sweep of the bow across the cello string. But here is where the story takes a turn into the truly strange. The mathematics of string theory are demanding. They are far more restrictive than the mathematics of points. When physicists first tried to write down the equations for these vibrating strings, they found something impossible. For the strings to vibrate in a way that produces the particles we see, to produce the specific mass and spin of the electron, they need room to move. They need degrees of freedom. In our familiar world, we have 3 dimensions of space, up, down, left, right, forward, backward. And we have 1 dimension of time, 4 dimensions in total. But when the strings tried to vibrate in only 3 spatial dimensions, the math collapsed. The equations produced anomalies, mathematical cancers that destroyed the theory. The strings were too constrained. They were like a dancer trying to perform a pirouette in a telephone booth. They kept bumping into the walls of reality. To make the math work, to make the music play correctly, the physicists had to do something radical. They had to add more dimensions. The equations whispered that for a universe of strings to exist, there must be 10 dimensions, or perhaps 11. Pause and try to hold this thought. 10 dimensions. We see 3. Where are the other 6? How can we be living in a 10-dimensional universe and only perceive a fraction of it? String theorists offer a poetic answer. The extra dimensions are curled up. They are compactified. Imagine looking at a garden hose lying on the grass from far away. It looks like a one-dimensional line. You can only move along it. But if you are an ant crawling on the hose, you realize there is a second dimension, the circular cross-section of the hose. You can walk around it. The second dimension is real, but it is small and curled upon itself. The 6 extra dimensions of string theory are like that circular cross-section, but they are curled up at every single point in space. At the tip of your nose, in the empty air, in the center of the sun, at every location, there are 6 tiny, invisible dimensions knotted together in complex shapes called Calabi-Yau manifolds. These shapes are incredibly beautiful. They look like twisted, multi-dimensional origami. And here is the crucial connection. The shape of these hidden dimensions determines how the strings vibrate. Imagine shouting into a cathedral. The sound echoes and resonates, shaped by the architecture of the room. Now imagine the string vibrating inside one of these tiny 6-dimensional Calabi-Yau shapes. The geometry of the shape dictates the resonance. It forces the string to vibrate in specific patterns. This means that the properties of the electron, its mass, its charge, and yes, its spin, are determined by the geometry of the hidden dimensions. The electron spins the way it does because the invisible universe forces it to. The music of reality is being played in a concert hall we cannot see, and we are just hearing the muffled notes that leak out into our 3 dimensions. This idea, known as compactification, suggests that the fundamental constants of nature are not random. They are geometrical. The number 1 over 137, the mass of the electron, the speed of light. These might all be consequences of the way the 6 extra dimensions are folded. If we could uncurl them, if we could look into that hidden space, we might see the true machinery of the cosmos. So, let us look at our electron again. It is no longer a point. It is a loop of vibrating energy, twisting through 10 dimensions. Its spin a reflection of a dance that happens mostly in a space we can never touch. It is a multi-dimensional traveler. There is a deep, resonant peace in this idea. It brings us back to Pythagoras, the ancient Greek philosopher who believed in the music of the spheres. He thought the planets moved in ratios that created a divine harmony. String theory tells us he was right, but he was looking at the wrong scale. The harmony is not in the planets. It is in the particles. The universe is a song. The electron is a persistent melody, a standing wave in the ocean of existence. And what conducts this orchestra? What plucks the strings? There is no player. The vibration is intrinsic. It is the nature of the energy itself to move, to oscillate. The universe is not a thing that contains music. It is music. It is vibration all the way down. But we must be careful here. We must be humble. String theory is intoxicatingly beautiful. It explains spin. It explains gravity. It unifies the forces. It is elegant, but it is also, so far, unproven. We have never seen a string. We have never peered into the 6th dimension. Our atom smashers are not powerful enough to probe these scales. Some critics call it fairy tale physics. They say we have wandered too far from the ground of experiment, lost in a mathematical dream world. They say we are like medieval monks arguing about how many angels can dance on the head of a pin, or, in this case, how many dimensions can curl on the head of a string. And yet, the spin of the electron beckons us. It points to something deeper than a point. The math of the point fails. The math of the string succeeds. Is beauty a guide to truth? Paul Dirac thought so. Einstein thought so. They believed that if an equation was ugly, it was wrong. String theory is the most beautiful theory we have. Does that make it true? As you lie in the quiet, consider the possibility that the solidity of the world is just a harmony of vibrations. The chair feels solid because the electromagnetic force is a loud, repulsive chord played by the strings of your body against the strings of the chair. The light is a soaring aria. The gravity that holds you to the bed is a deep bass hum of closed loops called gravitons. You are a chord. You are a complex, self-sustaining collection of vibrations, singing your existence into the void. And when you change, when you move, when you think, the music shifts. The symphony evolves. The mystery of electron spin has led us from a spinning top to a multidimensional cello. It has expanded our view of reality from 3 dimensions to 10. It has turned matter into music. But even string theory leaves a question unanswered. Why this music? Why these dimensions? Why is the string tension set exactly so? There is a sensation that comes when we push our minds this far, a feeling of vertigo, of standing on the edge of a cliff where human intuition falls away into the mist. We are asking questions that perhaps our brains are not wired to answer. We are middle-sized apes trying to reverse engineer the source code of the cosmos. And yet, we try. The spin compels us. It is the breadcrumb trail left by the universe, leading us deeper into the dark forest of understanding. In the next chapter, we will step back from the specific theories of strings and points and look at the information of the spin. We will look at a phenomenon that defies space and time entirely. We will look at entanglement. If 2 electrons interact and then separate, they remain connected. If you measure the spin of one, the spin of the other instantly snaps into the opposite state, even if it is on the other side of the galaxy. Einstein called it spooky action at a distance. He hated it. It seemed to break the rule that nothing travels faster than light. But it is real. The spin of the electron is not just a personal property. It is a shared destiny. It suggests that at some deep level, separation is an illusion. We are going to explore the idea that the universe is a hologram, that distance is a lie, and that everything is intimately connected to everything else. But for now, let the music of the strings lull you. Let the concept of the 10 dimensions expand your mind without breaking it. You are safe here, in your 3 dimensions, held together by the vibrations of the invisible. The electron spins, the string vibrates, the universe sings, and you are the listener. Rest in the harmony. We have walked a long road together through the landscape of the invisible. We have seen the electron dissolve from a hard sphere into a cloud, then into a mathematical spinner, and finally into a vibrating loop of 10-dimensional string. Each step has stripped away our common sense, replacing the solid world of our experience with a reality that is fluid, musical, and strange. But there is one intuition we have held on to, one belief that feels unshakable. The belief in separation. We believe that if 2 things are far apart, they are separate. If you are in your room and a star is 1 billion light-years away, you are distinct entities. To affect that star, you must send a signal, a beam of light, a radio wave, a spaceship, and that signal must travel across the vast ocean of distance, obeying the speed limit of the cosmos. This is the principle of locality. It is the rule that says things only interact when they touch, or when they send a messenger to bridge the gap. It is the rule that keeps the universe orderly. It prevents magic. It prevents telepathy. It keeps cause and effect in their proper lanes. But tonight, the electron is going to ask us to let go of even this. Tonight, we are going to look at the phenomenon that terrified Albert Einstein, the ghost that haunted his dreams and challenged his deepest convictions about reality. We are going to look at quantum entanglement, and we are going to discover that in the deep language of the spin, the word distance may have no meaning at all. To understand this, we must go back to the idea of the conservation of angular momentum. The universe is very strict about its accounting. It never loses spin. It never creates spin out of nothing. If you start with zero spin, you must end with zero spin. Imagine a particle, let us call it a pion, that has zero spin. It sits quietly in the void. Suddenly, it decays. It breaks apart into an electron and a positron. Because the original particle had zero spin, the total spin of the new pair must also add up to zero. If the electron spins up, the positron must spin down. They are born as a perfect, balanced pair. Now, imagine we let these two particles fly apart. We do not disturb them. We do not look at them. We just let them drift. One flies toward the Andromeda galaxy, 2.5 million light-years to the left. The other flies toward the Triangulum galaxy, 3 million light-years to the right. They are now separated by an abyss of space so vast that light would take millions of years to cross it. Here is the question. What is the spin of the electron? Based on what we learned in the early chapters, we know the answer. Until we measure it, the spin is not up or down. It is a superposition. It is a cloud of probability. The electron is 50% up and 50% down. And because the positron is its twin, it too is in a superposition. They are both undefined. They are both waiting. But they are not just waiting individually. They are waiting together. They share a single mathematical wave function. They are entangled. Now, suppose you are standing in the Andromeda galaxy with a Stern-Gerlach magnet. You catch the electron. You measure it. The universe forces a choice. The wave function collapses. The electron snaps into reality. Let us say it comes up spin up. At that exact instant, at the precise moment, you know the electron is up. What happens to the positron in the Triangulum galaxy? According to the laws of quantum mechanics, its wave function collapses instantly, without a single nanosecond of delay, without any signal crossing the space between them. The positron becomes spin down. It knows what happened to its twin. It knows the choice that was made across the universe, and it obeys the law of conservation by assuming the opposite state. This is what Einstein called spooky action at a distance. It made his skin crawl. To Einstein, this sounded like voodoo. It violated the sacred speed limit of light. How could the positron know? Did a message travel faster than light? Impossible. Relativity forbids it. Einstein argued that there must be a simpler explanation. He, along with his colleagues Boris Podolsky and Nathan Rosen, proposed a counter-argument known as the EPR paradox. They said, look, quantum mechanics is incomplete. It's missing something. They used the analogy of a pair of gloves. Imagine I have a pair of gloves, one left and one right. I put them in separate boxes. I mail one box to Andromeda and one box to Triangulum. I do not know which is which. When you open the box in Andromeda and see a left glove, you instantly know the other box contains a right glove. Is this spooky? No. Did a signal travel faster than light? No. The glove was always a left glove. From the moment it was packed, it was left. The only thing that changed was your knowledge. Einstein argued that particles must be like gloves. They must have hidden variables, secret instructions written inside them from the moment of their birth that tell them what to do. I am spin up, and you are spin down. They carry this reality with them. There is no magic communication. There is just pre-existing reality. This debate, gloves versus ghosts, raged for decades. Einstein wanted a universe of gloves, solid, real, defined, local. Niels Bohr and the quantum camp defended the universe of ghosts. Undefined, probabilistic, connected. But it was just philosophy. There was no way to tell who was right. The experimental results would look the same either way. One up, one down. Then came John Bell. John Bell was a physicist from Northern Ireland, a man with red hair and a piercing intellect, who worked at CERN in the 1960s. He was deeply sympathetic to Einstein. He wanted the world to make sense. He wanted to get rid of the spookiness. But he was honest. He sat down and asked himself, is there a difference between the gloves and the ghosts? Is there any experiment that could distinguish between Einstein's hidden variables and Bohr's quantum entanglement? He found one. It is now known as Bell's theorem, and it is widely considered one of the most profound discoveries in the history of science. The details are subtle, but the essence is this. If you measure the spins of the two particles, not just straight up and down, but at different angles, if you tilt your magnets, the gloves and the ghosts behave differently. If the particles are like gloves, with pre-written instructions, there is a limit to how correlated their spins can be when measured at different angles. There is a statistical ceiling. This limit is called Bell's inequality. But if the particles are truly quantum, if they are entangled ghosts that have no fixed state until measured, they can coordinate their answers in a way that breaks this limit. They can be more correlated than any independent objects could ever be. They can violate the inequality. Bell wrote down his theorem in 1964. It was a challenge to the experimentalists. Go check, he said. See if the universe obeys Einstein or Bohr. It took nearly 20 years to build the technology precise enough to do it. In the early 1980s, a French physicist named Alain Aspect performed the definitive experiment in Paris. He used lasers, calcium atoms, and extremely fast switches to measure the polarization of entangled photons, which works just like spin. He separated the detectors so that no signal traveling at the speed of light could pass between them during the measurement. The result was unequivocal. Einstein was wrong. The inequality was violated. The particles were more correlated than any hidden variable theory could explain. They were not gloves. They were not carrying secret instructions. They were truly, deeply, spookily entangled. Let the shock of this wash over you. The universe is not local. The positron in triangulum does not just happen to be down because the electron was up. It becomes down because the electron was measured. The choice made here determines the reality there. Space, the millions of light years of void, does not separate them in the eyes of the wave function. This suggests that distance is a macroscopic illusion. It is a rule that applies to big things like us, but not to the fundamental threads of reality. At the quantum level, the universe is a single, undivided whole. The electron and the positron are not two separate things. They are one thing stretched across a gap that we perceive as space. What does this mean for our concept of reality? It means that the separation we feel, the loneliness of the individual, is a trick of perspective. Think about the Big Bang. 13.8 billion years ago, all the matter in the universe was concentrated into a single point. Every electron, every quark, every photon was crushed together in a singularity of infinite density. They were all interacting. They were all entangled. Then the universe expanded. The particles flew apart. They formed stars, galaxies, planets, and you. But quantum mechanics tells us that entanglement is not easily broken. Once particles interact, they share a wave function. They remain connected until something disrupts that connection. This leads to a staggering poetic possibility. If everything interacted at the beginning, then everything is still entangled with everything else. The electrons in your left hand are entangled with electrons in a star on the edge of the observable universe. The atoms in your brain are entangled with the atoms in the dinosaurs deep underground. The web of connection is infinite and total. We act as if we are isolated islands, navigating a world of external objects. But the physics of spin tells us that underneath the surface, there are invisible threads linking every island to the ocean floor. We are part of a cosmic gelatin, a single quantum system that is breathing and evolving as one. This non-locality is the death of the idea of absolute separation. It suggests that when you look at a flower, you're not just seeing it. You are quantum mechanically related to it. When you look at the stars, you're not just an observer. You are a participant in their reality. But before we drift too far into mysticism, we must ground ourselves in the rigor of the science. Entanglement is real, but it is subtle. It does not allow us to send messages faster than light. You cannot use it to send a telegram to the Triangulum galaxy instantly. Why? Because the result of your measurement is random. You cannot force the electron to be up to send a 1 or down to send a 0. You can only measure what the universe gives you, and the universe gives you randomness. So, the correlation exists, but it cannot carry a human signal. Nature protects her speed limit. She allows the connection, but forbids the telephone call. It is a private line between the particles, not a public broadcast system. This limitation is frustrating to our desire for power, but perhaps it is beautiful for our contemplation. The connection is there, but it is silent. It is a bond of being, not a bond of doing. As you lie in the quiet of your room, think of the billions of entanglements passing through you right now. Think of the neutrinos streaming from the sun, the cosmic rays from distant supernovas, the radio waves from the Big Bang itself. They are all weaving through the lattice of your body, momentarily entangling with your electrons, linking you to the history of the cosmos. You are not a static object. You are a node in a neural network of light and matter that spans the entire universe. The spin of an electron in your fingertip might be the twin of a spin in the Orion Nebula. You are vast. You are extended. You are everywhere. This is the lesson of the ghost. Einstein wanted a universe of little marbles, each minding its own business, obeying local traffic laws. But the universe is a choir. When one voice sings, the others harmonize instantly across the dark. And this leads us to an even deeper question. If space is an illusion created by entanglement, what is space made of? Some modern physicists exploring the bleeding edge of the connection between quantum mechanics and gravity are starting to suggest that space itself, the very fabric we move through, is stitched together by entanglement. They call it ER, EPR. It is an equation that suggests a wormhole, an Einstein-Rosen bridge, and an entangled pair, EPR, are the same thing. They suggest that the gravity that holds you to the Earth is just the result of the massive entanglement of information. Space is not a stage. Space is the network of connections. If this is true, then spin is not just a property of matter. Spin is the needle that sews the quilt of space-time. The binary choices of up and down are the stitches that keep the universe from unraveling into chaos. We have come a long way from the spinning top. We have seen that the electron's spin is the guardian of solidity, Pauli, the child of relativity, Dirac, the dancer with light, Feynman, the note of a string theory, and now the bridge across the universe, entanglement. It is overwhelming, is it not? The mind struggles to hold all these concepts at once. But that struggle is the feeling of growth. It is the feeling of the brain stretching to accommodate the true scale of reality. Rest in the paradox. Rest in the spookiness. Do not be afraid of the connection. Embrace it. Feel the invisible threads radiating out from your chest, connecting you to the past, the future, and the farthest reaches of the dark. You are never alone, because at the quantum level, there is no such thing as alone. In the next chapter, we are going to turn our gaze from the single electron and the pair of electrons to the massive collections of them. We are going to look at how spin creates the most familiar yet mysterious force in our daily lives, magnetism. We all played with magnets as children. We felt the invisible spring pushing them apart, the snap as they pulled together. But have you ever wondered why a piece of cold iron can reach out and grab a nail? Why does the refrigerator magnet defy gravity? It is because the electrons, usually so chaotic and individualistic, decide to organize. They decide to dance in unison. We will see how the quantum spin, when synchronized across billions of atoms, creates a force powerful enough to lift trains and guide ships. We will move from the ghostly sociology of two particles to the political movement of the magnet. But for tonight, sleep with the knowledge of your entanglement. You are a citizen of a non-local universe. You are a part of the whole in a way that is not just poetic, but mathematically proven. The gloves are gone. Only the ghosts remain, and they are holding hands across the stars. We have spent the quiet hours of this night navigating the ghostly, ethereal landscapes of the very small. We have walked among isolated electrons, watched them shimmer in clouds of virtual light, and marveled at the invisible threads of entanglement that bind them across the galaxy. It has been a journey of the mind, a voyage into a world that, for all its beauty, feels distant from our daily experience. You cannot see an electron with your eyes. You cannot feel the texture of a wave function with your fingertips. The quantum realm usually stays hidden behind the curtain of the microscopic, doing its work in secret. But tonight, the curtain rises. Tonight, the ghostly spin of the electron steps onto the main stage of the visible world. It sheds its cloak of invisibility and manifests as a force you can hold in your hand. We are going to talk about the miracle of the magnet. Do you remember the first time you played with magnets as a child? Perhaps you had two dark, heavy rectangles of ferrite, or maybe the wooden trains with magnetic couplers. Do you remember the sensation of trying to push the two north poles together? It was a feeling unlike anything else in the world. It was not like pushing against a wall or a table where the resistance is hard and immediate. It was a soft, springy, escalating resistance. It felt as if there was something solid between them, something invisible but undeniably real. You could push and push, feeling the force grow stronger, fighting you, sliding sideways, refusing to yield. And then, if you flipped one magnet over, the resistance vanished instantly, replaced by a snap of attraction so fast and strong it could pinch your skin. That invisible spring, that silent snap, is the voice of the quantum spin. It is the collective shout of octillions of electrons, usually so chaotic and independent, suddenly deciding to sing in perfect unison. Magnetism is quantum mechanics writ large. It is the one place where the strange rules of the subatomic world amplify themselves enough to move a train, to lift a car, or to guide a compass needle across the trackless ocean. To understand why this is a miracle, we must first understand why it shouldn't happen. By all rights, the universe should be magnetically neutral. We learned earlier that electrons act like tiny bar magnets because of their spin. Every single electron in your body, in your chair, in the air you breathe, is a tiny magnet. So, why isn't everything magnetic? Why doesn't your spoon stick to the table? Why don't you stick to the door frame as you walk past? The answer lies in the intense desire of the universe for balance, and the specific rules of the Pauli exclusion principle we discussed. Electrons in an atom like to organize themselves in pairs. They inhabit the shells around the nucleus in couples. And just like a good marriage of opposites, if one electron spins up, its partner must spin down. The north pole of one cancels the south pole of the other. Their magnetic moments sum to zero. They neutralize each other. This is called diamagnetism, a weak repulsion that exists in almost all matter. But for our purposes, it means the magnetic magic is extinguished. The vast majority of atoms are magnetically silent because their electrons are locked in these canceling embraces. Even in atoms where there are lonely unpaired electrons, atoms that should be magnetic, the chaos of the everyday world usually wins. Imagine a block of aluminum. It has unpaired electrons. They are spinning. But they are like a crowd of people in a busy market square, facing in every random direction. One points left, one points right, one points up, one points down. The net result is noise. The sum of all those vectors is zero. The heat of the room jiggles them, preventing them from organizing. But then there is iron. Iron is special. Iron, along with its cousins nickel and cobalt, is the rebel of the periodic table. Deep inside the electron cloud of an iron atom, buried beneath the outer layers, there is a specific shell, the 3D subshell, that is incomplete. It has room for 10 electrons, but in iron, it only holds 6. Following the rules of quantum mechanics, 5 of them spin in one direction, and the 6th spins in the opposite direction. That leaves 4 electrons, 4 lonely, unpaired fermions, spinning in the same direction with no partners to cancel them out. This gives the iron atom a strong magnetic personality. But having a magnetic atom is not enough. You need the atoms to talk to each other. You need them to agree. In most materials, the atoms are too far apart, or the thermal energy is too high, and they ignore their neighbors. But in a crystal of iron, something magical happens. A quantum mechanical phenomenon called the exchange interaction kicks in. This is the secret handshake of ferromagnetism. It is a force that is not strictly magnetic, but arises from the Pauli exclusion principle and the electrical repulsion between electrons. Here is how it works. The electrons in neighboring iron atoms look at each other. They are fermions. They are stubborn. They want to avoid each other. The laws of quantum mechanics tell them that if they align their spins parallel to each other, if they all face up, they can stay further apart on average. By staying further apart, they reduce the electrical repulsion between them. It is a lower energy state. It is more comfortable. So, the electrons in the iron crystal whisper to their neighbors, if we all spin the same way, we can have more personal space. And the neighbors agree, and they whisper to their neighbors. A wave of consensus sweeps through the crystal. It is a quantum contagion. Suddenly, millions of atoms are locked in alignment, their spins pointing in the exact same direction, reinforcing each other, amplifying the tiny quantum effect into a massive macroscopic field. This is not a force field in the traditional sense. It is a social movement. It is the stillness of order, conquering the chaos of heat. However, if you pick up a normal iron nail, it acts like a magnet. But it is not a magnet. It doesn't stick to the fridge. Why? If the exchange interaction makes all the spins align, why isn't every piece of iron strictly magnetic all the time? The answer is that nature loves order, but she also hates broad, uncompensated fields of energy. A large magnetic field costs energy to maintain. So, the iron compromises. It divides itself into neighborhoods called vice domains, Imagine a map of a city. In one neighborhood, all the houses face north. In the next neighborhood, they all face east. In the third, they face south. Within each domain, which might be only a fraction of a millimeter across, the quantum alignment is perfect. Billions of atoms are singing in unison. But the domains themselves are randomly oriented. They cancel each other out. The nail is a patchwork of perfect order that sums to total chaos. This is the state of potential. The iron is sleeping. It has the capacity for power, but it is fragmented. Now, imagine you bring a strong permanent magnet close to that nail. You are introducing an external leader. You are introducing a field that says, north is this way. This external field exerts a pressure on the domains. The boundaries between the neighborhoods, the domain walls, begin to move. The domains that happen to be aligned with the magnet grow larger, eating their neighbors. They invade and conquer the territories of the misaligned domains. The atoms at the borders flip their spins, joining the winning side. It is a rapid, cascading conquest. Within moments, the entire nail has been unified. The chaos of the neighborhoods is gone. The vast majority of the electrons are now spinning in the same direction. The nail has become a magnet. It wakes up. It reaches out. It grabs the paper clip. This process, magnetization, is the awakening of the quantum army. It is the moment when the microscopic consensus becomes a macroscopic power, and the feeling you get when you pull the magnet away, that resistance, is the feeling of the magnetic field fighting to hold on to its new order, or in some cases, the domains snapping back to their chaotic rest. But this order is fragile. The enemy of magnetism is heat. Heat is vibration. Heat is the jiggling of atoms. As you heat a magnet, the atoms vibrate more and more violently. They shake in their lattice. The exchange interaction tries to hold them in line, tries to keep the spins parallel, but the thermal energy fights to randomize them. There is a specific temperature, unique to every magnetic material, called the Curie temperature, named after Pierre Curie, the husband of Marie Curie, and a giant of physics in his own right. For iron, this temperature is 1043 degrees Kelvin, or about 770 degrees Celsius. As you approach this temperature, the battle between quantum order and thermal chaos reaches a fever pitch. The domains start to fluctuate. The alignment wavers. And then, at the precise moment you cross the line, the battle is lost. The thermal energy overcomes the exchange interaction. The consensus breaks. The spins become random. The magnetism vanishes instantly. The iron forgets it was ever a magnet. It becomes paramagnetic, weak, confused, responding only slightly to the world. This transition is a phase change, just like ice melting into water. It is the melting of order. It reminds us that the forces that hold the world together are in a constant, delicate balance with the energy that wants to tear them apart. The magnet on your fridge exists only because your kitchen is cooler than 770 degrees Celsius. You are living in the quiet, cool valley where quantum order can survive. But let us expand our view from the nail to the planet. We live on a giant magnet. The Earth itself is a testament to the power of spin. Deep beneath your feet, nearly 2,000 miles down, lies the outer core. It is a vast ocean of molten iron and nickel, hot and fluid, swirling and churning. It is too hot to be a permanent magnet. It is far above the Curie temperature. The iron atoms there are jiggling too wildly to align by the exchange interaction. So, how does Earth generate its magnetic field? It uses a different trick. It uses the motion of the fluid itself. As the Earth spins on its axis, the Coriolis force twists the molten iron into great spiraling columns. Because the iron is hot and conducting, there are free electrons flowing through it. When you move a conductor through a magnetic field, you generate an electric current. And when you generate an electric current, you create a magnetic field. It is a self-sustaining loop, the geodynamo. The spin of the Earth creates the spirals create the currents create the magnetic field, and the magnetic field reinforces the currents. It is a majestic, rotating engine of electromagnetism that has been running for billions of years, and thank goodness it does. Because this field, born from the swirling spin of molten iron, reaches out into space, thousands of miles above our heads. It forms the magnetosphere, a great invisible shield that deflects the solar wind, the stream of deadly radiation and charged particles blasting from the sun. Without this shield, the solar wind would strip away our atmosphere. It would irradiate the surface. The oceans would evaporate. Life as we know it would be impossible. Mars, which lost its magnetic field billions of years ago, is a cold, dead, rusted desert. Earth, protected by its dynamo, is blue and green and alive. Think about this connection. The spin of the electron, amplified by the flow of molten metal, protected by the spin of the planet, creates the bubble of safety in which you sleep. We are cradled by magnetism. We are guarded by the giant, invisible arches of field lines that spring from the South Pole and dive into the North Pole. And sometimes we can see this shield. When the solar wind is particularly strong, it rattles the magnetosphere. Particles spiral down the field lines near the poles, crashing into the upper atmosphere. They excite the oxygen and nitrogen atoms, causing them to glow. This is the aurora borealis and the aurora australis, the northern and southern lights. If you have ever seen the auroras, those shimmering curtains of green and violet dancing in the night sky, you have seen the interaction of the sun's breath with the Earth's magnetic soul. You are seeing the shape of the magnetic field painted in light. You are watching the spin of the electrons in the upper atmosphere singing the song of protection. Magnetism is where the quantum world touches the human world most directly. It is in the compass that guided explorers to new continents. It is in the electric motors that power our civilization, for a motor is just magnets pushing against each other to create rotation. It is in the hard drives that store our knowledge, where tiny domains of magnetic material are flipped up or down to represent the ones and zeros of our digital lives, your memories, your photos, the words of this script. They are all stored as patterns of frozen spin on a platter of spinning metal. We have domesticated the electron's spin. We have taught it to remember for us. But there is a deeper resonance here. Magnetism represents the power of coherence. A single iron atom is weak. A single domain is microscopic. But when they align, when they act as one, they create a force that can bridge gaps and move mountains. It is a lesson from physics about the nature of unity. The force is not added from the outside. It emerges from the inside, from the agreement of the many to face the same way. As you lie in the dark, imagine the magnetic field lines of the Earth passing through the room right now. They pass through the walls, through the bed, through your body. They are undetectable to your senses, but they are there, steady and constant, pointing always north. You are lying in a river of invisible influence, and inside your body, your own electrons are spinning. They are not magnetic enough to align with the Earth. You are not made of iron, but they are aware. The nuclei of the hydrogen atoms in the water of your cells possess their own kind of spin, a nuclear spin. And while they are quiet now, we have found a way to make them speak, too. In the next chapter, we will take the ultimate step in our technological relationship with spin. We will look at how we use powerful magnets not to move metal, but to see inside the human body. We will explore magnetic resonance imaging, or MRI. We will learn how we can reach into the living tissue, grab the spins of your hydrogen atoms, tilt them, and listen to the radio song they sing as they stand back up. We will see how spin allows us to map the brain, to see thoughts forming, to heal the sick. We will move from the geology of the core to the biology of the mind. But for now, stay with the magnet. Remember that feeling of the invisible spring. Remember the snap of connection. It is the universe telling you that empty space is not empty. It is woven with fields. It is tense with potential. And it is all generated by the tireless, eternal, quantized rotation of the tiny entities that make up the dust, the stars, and the hand that holds the magnet. The electron spins, the iron aligns, the shield holds. And the night is safe. We have journeyed from the molten iron core of our planet, churning 2,000 miles beneath our feet, to the protective shield of the magnetosphere, dancing in the polar skies. We have seen how the spin of electrons, when aligned in vast numbers, creates the invisible power that guides, compasses, and shields life. But now, I want to invite you into a different kind of room. It is not a laboratory in 1920, and it is not a theoretical space of 10 dimensions. It is a room you may have visited yourself. It is stark, white, and cold. In the center sits a massive, donut-shaped machine, humming with a sound that feels less like a motor and more like a trapped beast. We are standing in the presence of a magnetic resonance imaging scanner, an MRI. For many, this machine is a place of anxiety. It is tight, loud, and claustrophobic. You lie on a narrow table, are slid into the throat of the device, and are told to hold perfectly still while the machine bangs and clatters around you like a construction site. But tonight, I want to strip away the fear and show you the magic. I want you to see this machine not as a medical device, but as a quantum observatory. When you enter an MRI, you are placing your body inside the largest, most powerful application of spin theory ever built by human hands. You are entering a cathedral where we force the atoms of your own body to sing to us. To understand how we see inside you without a knife, we must shift our focus slightly. Throughout this night, we have spoken mostly of the electron. But the electron is not the only thing that spins. Deep in the center of the atom, the nucleus also possesses angular momentum. In the case of hydrogen, the most common element in the universe, and in your body, the nucleus is a single proton. And just like the electron, the proton is a fermion. It has spin 1/2. It has a magnetic moment. It is a tiny subatomic compass needle. You are mostly water. Roughly 60% of you is H2O. That means you are a walking vessel of hydrogen. You contain octillions of protons, each one spinning, each one acting like a microscopic magnet. Under normal circumstances, as you sit here in your room, these proton magnets are pointing in random directions. They are disordered, canceling each other out, just like the domains in a piece of unmagnetized iron. You are magnetically neutral. But when you slide into the bore of the MRI scanner, you are entering a magnetic field of terrifying strength. The magnets in these machines are superconducting coils cooled by liquid helium to near absolute zero. They generate a field tens of thousands of times stronger than the magnetic field of the Earth. In this intense grip, the protons in your body snap to attention. They do not all point exactly the same way. Thermal energy still jiggles them, but a small, significant fraction of them align with the field. They stand up. They face north. Suddenly, for the duration of the scan, you become magnetized. You become a polarized object. The chaos of your biological matter is brought into a temporary, disciplined order by the brute force of the external field. But a static field acts only as a frame. It creates the stage, but it does not create the image. To see the protons, we have to disturb them. We have to make them move. This is where the resonance in magnetic resonance imaging comes into play. It is a concept of pure musicality. Every spinning object has a natural frequency at which it likes to wobble. If you have ever spun a top, you have seen this. As the top spins, its axis slowly circles around the vertical. This slow, rhythmic wobble is called precession. The protons in your body, trapped in the massive magnetic field, are precessing. They are wobbling at a very specific speed, known as the Larmor frequency. For a standard MRI machine, this frequency is in the range of radio waves, about 60 to 100 megahertz. It is the same kind of frequency used by FM radio stations. So, the machine waits until your protons are aligned, and then it fires a pulse. It is not a laser or an X-ray. It is a pulse of radio waves, but not just any radio waves. The machine is tuned precisely, exquisitely, to the Larmor frequency of your hydrogen atoms. It sings the exact note that your protons want to hear. When this radio pulse hits your body, the protons absorb the energy. They resonate. They tip over. Imagine a field of wheat standing tall in the wind. The radio pulse is a gust that pushes them all over onto their sides. They are still spinning, but now they are spinning on their sides, rotating in sync, creating a magnetic signal that sweeps around like the beam of a lighthouse. Then the machine stops the pulse. Silence returns. And this is the moment of magic. This is the moment the ghost speaks. The protons, no longer being pushed by the radio waves, begin to stand back up. They begin to relax, returning to their original alignment with the main magnetic field. As they stand up, they release the energy they borrowed from the radio pulse. They emit a radio wave of their own. Your body becomes a radio transmitter. Your liver, your brain, your heart, your knees, they all broadcast a signal back to the machine. It is a faint quantum echo. I am here, the protons say. I am standing back up. But here is the genius of the technology. Not all protons stand up at the same speed. The rate at which they relax depends on their environment. A hydrogen atom in a molecule of water relaxes at a different speed than a hydrogen atom in a molecule of fat. A proton in a healthy brain cell relaxes differently than a proton in a tumor. The chemical neighborhood changes the magnetic struggle. The computer listens to this chorus of radio signals. It hears the fast relaxation of fat and the slow relaxation of water. It distinguishes the subtle magnetic textures of bone and blood. And using complex mathematics, it converts these time differences into shades of gray. It paints a picture. When you look at an MRI image, you're looking at a map of proton relaxation times. You are seeing the molecular difference between tissue types, translated into light and dark. You are seeing the quantum spin of the hydrogen nucleus, revealing the architecture of life. Think about the intimacy of this. We are not looking at the surface of the body. We are not casting a shadow like an X-ray. We are reaching into the very core of the atoms, tilting them, and listening to their struggle to return to rest. We are using the fundamental spin of matter to diagnose a torn ligament or a blocked vessel. And the noise, the banging and clanging that terrifies so many patients, that is the sound of the gradient coils to make a 3D image We cannot just listen to the whole body at once. We have to know where the signal is coming from. So, the machine rapidly changes the magnetic field, making it slightly stronger at your head than at your feet, then stronger on the left than the right. By tweaking the field, we change the resonant frequency of the protons in different slices of your body. We tune the notes of your body like a piano, playing one slice at a time. The banging sound is the physical slam of metal coils expanding and contracting as immense electrical currents are switched on and off to shape the magnetic field. It is the percussion section of the quantum orchestra. This technology allows us to do something even more profound than seeing anatomy. It allows us to see thought. In a technique called functional MRI, or fMRI, we look at the blood. Blood contains hemoglobin, the molecule that carries oxygen. Hemoglobin has iron in it, and just like the iron in the nail, the magnetic properties of hemoglobin change depending on whether it is holding oxygen or not. Oxygenated blood is diamagnetic. Deoxygenated blood is paramagnetic. They affect the local magnetic field differently. When you think, when you use a part of your brain, say, the part that processes vision, that area works harder. It needs more energy. The body rushes fresh, oxygenated blood to that specific spot. The fMRI scanner is sensitive enough to see this subtle change in the magnetic signature of the blood. It can see the rush of oxygen to the active neurons. So, we can put you in the scanner and show you a picture of a flower. And, on the screen, we can see a tiny patch of your visual cortex light up. We can ask you to think about moving your hand, and we see the motor cortex glow. We are watching the metabolic shadow of consciousness itself. We are mapping the geography of the mind using the magnetic spin of iron and hydrogen. It is a staggering realization. The spin of the electron, discovered in the abstract math of Paul Dirac, and the spin of the proton, a fundamental property of the nucleus, are the tools we use to understand ourselves. The mystery of the subatomic has become the mirror of the self. There is a deep philosophical beauty in the safety of the MRI. Unlike X-rays or CT scans, which use ionizing radiation that can damage DNA, the MRI uses only magnetic fields and radio waves. It is non-invasive. It is gentle. It passes through you without leaving a trace. It respects the biological integrity of the subject. It is a dialogue, not a bombardment. It reminds us that we are transparent to the forces of the universe. We feel solid, but to a magnetic field, we are just a cloud of suspended spins waiting to be aligned. We are permeable. We are open systems. As you lie in the quiet of your room, imagine the trillions of protons in your body. They are not aligned right now. They are tumbling and precessing in the gentle, weak magnetic field of the earth. They are disorganized. But they hold the potential for that alignment. They hold the potential to sing that radio song if called upon. You are a silent orchestra. You are a library of unread books, written in the ink of spin. This technology is perhaps the ultimate triumph of the shut up and calculate era of quantum physics. We may not intuitively understand what spin is. We still struggle with the image of the rotating point. But we understand it well enough to build a machine that can find a tumor in a child's brain without cutting their skin. We understand it well enough to save lives. The abstraction has become salvation. The weirdness has become a tool. But the journey of spin is not just about looking inward at the body. It is also about looking forward to the future of information itself. We live in a digital age, powered by bits of ones and zeros stored on magnetic drives. But the binary world of the classical computer is reaching its limit. The silicon chips are getting too small. The heat is getting too high. We are hitting the wall of atomic physics. To go further, we must return to the source. We must return to the superposition. We must return to the idea that a particle can be up and down at the same time. In the next chapter, we will leave the hospital and enter the frozen, gold-plated chambers of the quantum computer. We will look at the qubit. We will see how we are trying to harness the ghostly, indeterminate nature of spin, not just to store data, but to process it in ways that defy classical logic. We are trying to build a brain out of individual atoms. We are trying to build a machine that thinks in the language of the multiverse. We will explore how spin could allow us to simulate new medicines, design new materials, and perhaps solve problems that would take a normal computer the age of the universe to crack. We are moving from the passive observation of spin, MRI, to the active manipulation of quantum reality, quantum computing. But for now, remember the sound of the MRI. That rhythmic banging is not just noise. It is the sound of humanity knocking on the door of the quantum world, asking it to reveal its secrets. And the image on the screen, the black and white cross-section of a beating heart, is the answer. It is the spin saying, I am here, I am you. Rest in the wonder of your own transparency. Rest in the knowledge that your atoms are capable of such beautiful resonance. You are not just matter. You are music waiting to be played. We have walked through the doors of the hospital and left the rhythmic banging of the MRI machine behind us. We have seen how the spin of the hydrogen nucleus allows us to peer inside the human body, turning the invisible magnetic whispers of our atoms into images of life. But our journey into the utility of spin is not over. In fact, we are about to leave the realm of mere observation and enter the realm of creation. We are going to look at how humanity is attempting to harness the ghost of the electron to build a new kind of mind. To do this, we must travel to a place that looks more like an art installation than a laboratory. Imagine a room that is perfectly clean, silent, and vibrating with a hum of high-performance pumps. Hanging from the ceiling is a strange, beautiful object. It looks like an elaborate, multi-tiered chandelier made of gleaming gold and copper, a cascading structure of pipes and coils that narrows as it descends. This is a dilution refrigerator, and inside the bottom of this golden chandelier, in a space no larger than a soup can, is one of the coldest places in the entire universe. It is colder than the deep void between the galaxies. It is cooled to within a fraction of a degree of absolute zero. Why do we need such extreme cold? Because we are trying to isolate the most fragile thing in existence. We are trying to protect a qubit. For the last 70 years, our civilization has been built on the back of the classical bit. Every computer, every smartphone, every internet server operates on a simple binary logic. A switch is either on or off. A voltage is either high or low. A bit is either 1 or 0. This logic is robust. It is reliable. It has allowed us to land on the moon and map the human genome. But it is fundamentally limited. It is a linear way of thinking in a nonlinear universe. The classical bit is like a coin glued to a table. It is either heads up or heads down. There is no middle ground. But we have learned tonight that the electron does not play by these rules. We know that the spin of an electron, before it is measured, exists in a superposition. It is a cloud of probability. It is a mixture of up and down at the same time. Enter the quantum bit, or qubit. A qubit is not a coin glued to a table. A qubit is a spinning sphere. Imagine the Earth. The North Pole represents 1. The South Pole represents 0. A classical bit can only be at the North Pole or the South Pole. But a qubit can be anywhere on the surface of the sphere. It can be on the equator. It can be in the tropics. It can be at 45 degrees longitude. It can encode an infinite number of states between 0 and 1. When we use the spin of an electron, or a superconducting circuit mimicking an artificial atom as a qubit, we are unlocking a computational power that defies intuition. Because the qubit exists in a superposition of states, it allows the computer to hold multiple possibilities in its memory simultaneously. But the real magic happens when we bring back our old friend from the previous chapters, entanglement. If you have 2 classical bits, you can have 4 possible combinations: 0, 0, 0, 1, 1, 0, or 1, 1. But at any given moment, the computer can only be in one of those states. It has to choose. If you have 2 entangled qubits, however, they can exist in a superposition of all 4 states at once. They are a complex, woven tapestry of probabilities. If you add a 3rd qubit, you can hold 8 states. If you add a 4th, 16. The power grows exponentially. By the time you have just 300 entangled qubits, a number that seems small, you can hold more simultaneous states than there are atoms in the observable universe. 300 spinning particles can contain more information than all the matter in the cosmos. This is the promise of the quantum computer. It is not just a faster version of the laptop on your desk. It is a different kind of machine entirely. It is a machine that explores parallel realities. When a quantum computer solves a problem, it does not check the answers one by one like a classical computer. It enters a state where all possible answers exist in a superposition. And then, using the wave-like nature of quantum mechanics, it interferes the wrong answers out of existence, amplifying the probability of the right answer until it emerges as the only reality. It is like a maze solver that does not run down one corridor, hit a dead end, and turn back. It pours water into the maze. The water explores all paths simultaneously, instantly finding the exit. But why do we need this? Why go to the trouble of building golden chandeliers and freezing atoms to absolute 0? We need it because nature is quantum. This was the insight of Richard Feynman in 1981. He famously said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical." Think about a caffeine molecule. It is a simple drug that wakes you up in the morning. It has only 24 atoms. But to simulate the interactions of those 24 atoms perfectly, to model the spins of all the electrons and how they push and pull on each other, requires a computer memory larger than any classical supercomputer that can ever be built. The complexity of the electron dance is too great. The many-body problem, the problem of how many particles interact, overwhelms binary logic. But a quantum computer is nature. It speaks the native language of the molecule. It can simulate the caffeine molecule because it operates on the same principles of spin and superposition. This means that with a functioning quantum computer, we could design new medicines not by trial and error in a lab, but by perfect simulation. We could invent materials that conduct electricity with 0 resistance. We could design catalysts that pull carbon dioxide out of the air as efficiently as a leaf. We could solve the riddle of nitrogen fixation to feed the world without polluting it. We could unlock the secrets of high-temperature superconductivity. We are trying to build a brain that can understand the quantum weave of reality because it is made of that weave. But there is a catch. There is always a catch. And in the world of quantum computing, The catch has a name: decoherence. Remember how fragile the superposition is. Remember how the electron snaps into a fixed state the moment it interacts with the environment. This is the enemy of the quantum computer. The qubit is incredibly shy. It wants to do its magical multi-state calculation in private. But the universe is noisy. A stray photon from the room lights, a slight vibration from a passing truck, a fluctuation in the Earth's magnetic field, even a cosmic ray from deep space. Any of these can touch the qubit. And the moment the environment touches the qubit, the magic collapses. The superposition vanishes. The qubit becomes a boring classical bit. The calculation fails. This is decoherence. It is the universe trying to peek at the answer before the computer is finished. This is why the machines are so beautiful and so isolated. The golden chandelier is a fortress of solitude. The vacuum chambers are pumped to pressures lower than outer space. The magnetic shielding is impenetrable. We are trying to create a tiny pocket of the universe where the noise of reality is silenced, where the spin can dance its complex dance without being stepped on. It is a battle between human engineering and the second law of thermodynamics. We are trying to maintain a state of perfect quantum order in a universe that tends toward messy disorder. It is the hardest engineering challenge our species has ever undertaken, and yet we are doing it. We have machines now with 50, 60, 100 qubits. They're noisy. They make mistakes. They are like the first vacuum tube computers of the 1940s. Huge, fragile, and limited. But they work. We have reached a milestone called quantum advantage, where a quantum computer performed a calculation in minutes that would have taken a classical supercomputer thousands of years. The calculation was useless. It was just a random sampling problem, but it was a proof of concept. The ghost is in the machine. The spin is doing the work. As you lie there, consider the philosophical weight of this. We are harnessing the undefined nature of reality to define our future. We are using the fact that an electron is not a specific thing to do specific work. We are monetizing the mystery. There is a sense in which the quantum computer forces us to confront the nature of the multiverse. When the computer is in that superposition of a trillion states, where are those states? David Deutsch, a pioneer of quantum computing, argues that they are real. He argues that the quantum computer is actually performing calculations in parallel universes and recombining the results in ours. He says that the immense power of the machine is proof that the multiverse exists. Whether you believe in parallel universes or just in the abstract power of the wave function, the implication is the same. The resources available to us in the quantum realm are vastly larger than the resources of the visible, classical world. We have been computing with the shadows of reality. Now, we are learning to compute with the source. And what creates this power? Spin, the simple half-integer angular momentum of the fermion, the up and the down, and the beautiful, complex space in between. We are building a cathedral to the spin. We are encoding our problems into the rotation of atoms and asking the universe to spin them into answers. But this technology brings us back to a feeling of humility. We are not inventing these rules. We are discovering them. The electron has been capable of this for 13.8 billion years. Every atom in a stone has the potential for this complexity. We are just now learning how to ask it to perform. As we near the end of our journey, the room around you feels different, does it not? It is not just a room of wood and plaster. It is a room of potential. The air is alive with the same physics that powers these golden machines. The warmth of your body is generated by chemical reactions that are, at their core, quantum mechanical exchanges of spin. You are a quantum machine. Your biology has evolved to navigate this fuzzy, noisy world, but deep down, your DNA is held together by the same rules that we are struggling to trap in our dilution refrigerators. Some biologists even speculate that birds navigate using quantum entanglement in their eyes, seeing the magnetic field lines of the Earth through the spin of electrons in a protein called cryptochrome. Life may have figured out quantum computing billions of years before we did. So, the golden chandelier is not an alien artifact. It is a mirror. It is us trying to build a machine that works the way the universe actually works. In the next chapter, we will step back from the technology and return to the cosmos. We will look at the ultimate test of our understanding. We have talked about the very small. Now we must talk about the very dense. We are going to visit the place where spin fights its final battle against gravity. We are going to visit the neutron star and the black hole. We will see what happens when the exclusion principle is pushed to the breaking point. We will see stars that spin faster than a kitchen blender. We will see the event horizon, where information, including the information of spin, might be lost forever. We will stand on the edge of the abyss and ask if the spin survives the end of space and time. But for now, rest in the promise of the qubit. Rest in the idea that the universe has infinite capacity for imagination, and that by tapping into the spin, we are learning to dream with it. The golden chandelier hangs in the dark, cold, and silent, a beacon of the future powered by the oldest motion in existence. We have left the frozen silence of the quantum computer, that golden sanctuary where we try to coax the electron spin into performing calculations in a whisper. We have seen how delicate the quantum state is, how easily it shatters when touched by the warmth of the world. But the universe is not always gentle. It is not always a place of absolute zero and careful isolation. In the deep dark, far from the safety of our solar system, there are places where the laws of physics we have discussed, the exclusion principle, the conservation of angular momentum, the resistance of fermions, are tested in a crucible of violence so extreme that it defies the human capacity for visualization. Tonight, we travel to the graveyard of the stars. But do not be afraid. In the cosmos, a graveyard is also a monument. It is where the spin of matter fights its final, desperate battle against the crushing hand of gravity. We are going to visit the neutron star and the black hole. Imagine a star much larger than our sun, a massive giant burning blue and hot for millions of years. It is a spinning ball of gas, rotating majestically once every few weeks. It is held up by the heat of its nuclear fusion, pushing out against the gravity, pulling in. But eventually, the fuel runs out, the fire dies, and gravity, which never sleeps and never tires, takes over. The star begins to collapse. It falls in on itself. The outer layers are blown away in a supernova explosion, a flash of light brighter than a galaxy. But the core, the heart of the star, remains, and it shrinks. It shrinks from a sphere 1,000,000 miles wide to a sphere the size of a small city. Imagine the entire mass of the sun compressed into the space of Manhattan Island. In this crushing descent, the electrons in the star are panicked. As the space gets smaller, they are squeezed closer and closer together. Remember the Pauli exclusion principle. Remember the stubbornness of the fermions. The electrons scream, "We cannot be this close. Our quantum states are full." They push back with electron degeneracy pressure. This force is enough to hold up a white dwarf star. But in these massive giants, gravity is too strong. It breaks the electron's will. The pressure becomes so intense that the electrons are forced to do the unthinkable. They are smashed into the protons. The negative merges with the positive. They cancel each other out. The electrons disappear. The protons disappear. All that is left are neutrons, neutral fermions that can be packed even tighter. The star becomes a neutron star. It is a ball of pure nuclear matter, a city-sized atomic nucleus. A single teaspoon of this material would weigh 1 billion tons. If you dropped that teaspoon on Earth, it would punch through the crust and fall straight to the core. But here is where the spin returns to the story, more powerful than ever. The original star was spinning. It had a massive amount of angular momentum. As it collapses, that momentum cannot be lost. It must be conserved. Think of the ice skater pulling her arms in. As she shrinks her profile, she spins faster. The star pulls its arms in from 1,000,000 miles to 10 miles. The result is a rotation speed that terrifies the imagination. The star, which once turned lazily once a month, now spins hundreds of times per second. Imagine a sphere of solid nuclear matter, heavier than the sun, spinning at 700 revolutions per second. The surface is moving at a significant fraction of the speed of light. The centrifugal force is immense, flattening the star into a slightly oblate shape. But the gravity is so strong that it holds the star together, maintaining a surface smooth to within a few millimeters. This is a pulsar. It is a cosmic lighthouse. The magnetic field of the star, also compressed and amplified to trillions of times the strength of the Earth's field, beams radiation out from the poles. As the star spins, these beams sweep across the universe. If the Earth happens to be in the path of the beam, we see a pulse of radio waves every time the star rotates. Beep, beep, beep. When Jocelyn Bell Burnell first discovered these pulses in 1967, she thought they might be signals from an alien civilization. They were too regular, too precise to be natural. She labeled the signal LGM-1 for little green men. But it was not aliens. It was spin. It was the frantic clockwork rotation of a dead star, broadcasting its existence to the cosmos with the precision of an atomic clock. We can listen to these pulsars. Astronomers convert the radio waves into sound. The slower ones sound like a rhythmic thumping, thump, thump, thump. But the fast ones, the millisecond pulsars, spin so fast that the individual thumps blur together into a hum, a low, musical note. The universe is literally singing with the vibration of these spinning giants. The neutron star is the ultimate triumph of the Pauli exclusion principle. The neutrons, being fermions, refuse to occupy the same state. They exert neutron degeneracy pressure, creating a hard floor that stops the collapse. They hold the line against gravity. They say, this far and no farther. But sometimes gravity is too strong. Sometimes the dying star is just a little bit too heavy. If the core remains more than about 3 times the mass of the sun, even the neutrons cannot hold the line. The exclusion principle is overwhelmed. The floor breaks. The collapse continues. The city-sized ball shrinks to the size of a village, then a house, then a walnut, then a pea. It crosses a boundary called the event horizon, the point of no return. The escape velocity exceeds the speed of light. The star vanishes from the visible universe. It becomes a black hole. In the popular imagination, a black hole is a hole. It is a drain. It is a point of infinite density called a singularity, where space and time end. And if the black hole were not spinning, this would be true. The singularity would be a point, a dimensionless dot at the center. But stars always spin, and when they collapse into black holes, they keep spinning. And because a black hole has no surface to slow it down, no air to create friction, it spins forever. A spinning black hole is a very different beast from a stationary one. It is called a Kerr black hole, named after Roy Kerr, the New Zealander mathematician who solved the equations for it in 1963. And what he found changes everything we think about space. When a black hole spins, it does not just spin within space. It grabs the fabric of space-time and drags it along with it. Imagine a ball spinning in a bowl of thick honey. As the ball turns, the honey around it begins to turn as well. The honey near the surface of the ball spins fast. The honey further away spins slower. Space-time is the honey. This phenomenon is called frame dragging. Around a spinning black hole, space itself is rotating. If you were floating near a spinning black hole, you would find yourself being dragged around it, orbiting the center, even if you tried to hover perfectly still. You're not moving through space. Space is moving you. There is a region around the black hole called the ergosphere, where this dragging becomes absolute. In this region, space is being dragged around the black hole faster than the speed of light. Think about that. Space can move faster than light because space is not a thing that has mass. Inside the ergosphere, it is physically impossible to stand still. No rocket engine, no matter how powerful, could keep you stationary. You must spin. You must join the dance. To stand still would require moving faster than light relative to the space around you, which is impossible. You can still escape the ergosphere. You can fly out. But while you are in it, you are a prisoner of the spin. You are flowing in a river of twisted time. And what happens at the center? What happens to the singularity? If the star collapses while spinning, the centrifugal force prevents the matter from crushing down into a single point. It fights against the inward pull. The result is that the singularity is not a dot. It is a ring singularity. It is a circle of zero thickness, but non-zero radius, spinning at the heart of darkness. It is a gateway of infinite density, but it has a shape. This leads to some of the wildest speculations in physics. Because the singularity is a ring, it might be possible, mathematically at least, to fall through the center of the ring without hitting the singularity itself. You would pass through the eye of the storm. Where would you go? The equations of general relativity suggest that you might emerge into a region of negative space, or perhaps into another universe entirely. A wormhole, a bridge. The spinning black hole might not be a dead end, but a door. We must be careful here. These are mathematical possibilities, not proven travel guides. The inside of a black hole is a place of extreme violence, where tidal forces would likely rip any traveler apart long before they reach the ring. But the mere existence of the ring singularity shows us that spin changes the fundamental geometry of the end of the world. It turns a period into a comma. There is something profoundly haunting about the black hole. When a star collapses, it destroys everything. It crushes its atoms. It destroys its chemical composition. It erases the difference between gold and lead, between gas and rock. It destroys the structure of matter itself. But it preserves three things. Only three things survive the collapse to become properties of the black hole. One is mass, the total amount of stuff. Two is charge, the electrical state. Three is spin, the angular momentum. That is the no-hair theorem. A black hole has no hair. It has no complex details. It is simple. It is defined only by mass, charge, and spin. Everything else, the color of the star, the history of its planets, the shape of its magnetic fields, is gone. But the spin remains. The rotation of the ancient star is preserved in the geometry of the dark space-time. It is a memory that cannot be erased. As you lie in the quiet of your room, consider this endurance. The electron in your finger has spin. That spin is a fundamental property that connects it to the relativistic equations of Dirac. If you were to fall into a black hole, a thought experiment only, please, your body would be destroyed. Your atoms would be crushed. But your angular momentum, the total spin of all your particles, would be added to the black hole. You would make it spin just a tiny bit faster. Your rotation would become part of the eternal rotation of the abyss. Spin is, in a sense, immortal. It is a quantity that the universe refuses to lose. It can be transferred, it can be hidden, it can be absorbed, but it cannot be destroyed. This journey to the extremes of gravity brings us back to a sense of scale. We started with a tiny, point-like electron that had to spin twice to return to its original state. We ended with a hole in the universe that drags space around it like a whirlpool, with a ring of infinite density at its heart. And yet, they are connected. The black hole is just the macroscopic accumulation of the properties of the microscopic. The exclusion principle that fights the collapse is the same exclusion principle that keeps your chair solid. The spin of the black hole is the sum of the spins of the particles that made it. The universe is one thing. The laws that govern the smallest speck are the laws that govern the monsters in the dark. We have seen spin as a label, as a cloud, as a magnet, as a computer, and now as a geometric tornado. It is the thread that weaves the tapestry together. It is the motion that defines existence. As we approach the end of our night together, we must prepare to return to the human scale. We have floated in the void long enough. We need to bring these concepts back home, to the body breathing in the bed, to the mind wandering in the dark. In the final chapter, we will try to synthesize all we have seen. We will ask what it means to be a spinning creature in a spinning universe. We will look at the spin not just as a physical quantity, but as a metaphor for the cycles of our lives, for the return of the seasons, for the way we orbit our own centers. We will gently close the book of physics and open the book of being. We will find that the mystery is not something to be solved, but something to be lived. But for now, leave the black hole spinning in the distance. Let the gravity fade. Let the time dilation relax. You are back on Earth. You are back in the safe, weak gravity of our home. You are back in the gentle magnetic field that points north. You are safe. But you are spinning. You are always spinning. We have returned. The event horizon of the black hole has faded into the distance, and the terrifying gravity of the neutron star has released its grip on our imagination. We are back in the quiet safety of the room where we began. The shadows in the corner are just shadows, not dark matter. The silence is just the absence of sound, not the vacuum of deep space. And yet, I hope that the room feels different to you now. I hope that the stillness you feel is no longer an empty stillness, but a vibrant, humming suspension, like a gyroscope spinning so perfectly fast that it appears to be standing stone still. We have traveled from the incomprehensible vastness of the galaxy down to the invisible knot of the string, and everywhere we looked, we found the same thing. We found the turn. We found the loop. We found the spin. It is time to ask the final question, the question that bridges the gap between the notebook of the physicist and the heart of the human being. Why? Why does the universe choose this motion above all others? Why is the fundamental building block of reality not a static brick, but a pirouetting dancer? Throughout this journey, We have seen that linear motion, moving in a straight line, is the motion of departure. If you travel in a straight line, you leave, you go away, and unless you change course, you never come back. Linear motion is the motion of abandonment. But spin is the motion of return. To spin is to constantly come back to where you started. It is the geometry of the cycle. It is the geometry of memory. Think about this on a cosmic scale. If the universe only had linear momentum, everything would just fly apart. Atoms would never form. They would just rush past each other. Solar systems would never coalesce. The universe would be a dispersing mist of lonely particles, fleeing from one another into the dark. But because of angular momentum, because of spin, matter can clump. It can fold in on itself. It can orbit. It can build. The electron spins around the nucleus, and the atom is born. The moon spins around the earth, and the tides are born. The earth spins around the sun, and the year is born. Spin is the promise that things will not just drift away. It is the promise of structure. It is the force that allows the universe to hold on to itself. This connects deeply to a beautiful idea in physics known as Noether's theorem, named after the brilliant mathematician Emmy Noether. She proved that every conservation law in the universe comes from a symmetry. The conservation of energy comes from the fact that physics is the same today as it was yesterday. And the conservation of angular momentum, the law that keeps the electron spinning and the black hole turning, comes from the fact that space is isotropic. It means that the universe has no preferred direction. Facing north is no better than facing south. Because space is the same in all directions, rotation is conserved. This means that the spin of the electron is a direct consequence of the fairness of space. Because the universe treats every direction equally, it gifts its particles with the ability to turn forever. The democracy of the void creates the eternity of the spin. As you lie here, you are a beneficiary of this fairness. The stability of your body, the persistence of your heartbeat, the cycle of your breath, these are all macroscopic echoes of that fundamental principle. You are a collection of cycles. You are a biological system built on the premise of return. Blood leaves the heart to return to the heart. Air leaves the lungs to return to the lungs. Thoughts leave the silence to return to the silence. We often think of progress as a straight line, a ladder we climb, but the wisdom of the electron suggests otherwise. It suggests that existence is not a line, but a spiral. We move forward, yes, but we also circle back. We revisit the same lessons. We see the same seasons. We wake up and we go to sleep. The spin is the mechanism of renewal. Without it, there would only be a beginning and an end. With it, there is a middle. There is a story. We started this journey with a paradox. The electron acts like it is spinning, but it is too small to actually spin. We tried to solve it with the cloud of probability, with the Dirac equation, with the quantum field, and with string theory. And in a way, we solved it. We found the math that describes it. But in another way, the mystery remains. We know how it works, but the what, the fundamental stuff that is spinning, remains elusive. And perhaps that is exactly how it should be. If we could explain everything, if we could dismantle the universe into a set of dry mechanical gears, we might lose the sense of wonder that drives us. The hiddenness of the spin is what invites us to keep looking. It is what keeps science alive. It is what keeps us humble. There is a concept in ancient philosophy, found in traditions from the Sufi mystics to the Taoists, that the center of the wheel is the most important part, because it is the part that does not move. The hub is the anchor. The electron has a center. The atom has a nucleus. The solar system has a sun. The galaxy has a black hole. Everything that spins turns around something. What is your center? As you navigate the spinning chaos of the world, the traffic, the news, the noise, the demands of your time, what is the axis that you turn around? Tonight, I want to suggest that your consciousness, your awareness, is that axis. The part of you that is listening to these words right now is the witness. It is the stillness in the center of the storm. Your thoughts are spinning. Your emotions are swirling like the clouds of a gas giant. Your body is vibrating with thermal energy. But the you behind it all, the you that observes, is the quiet singularity. Physics tells us that motion is relative. You can only say you are moving if you compare yourself to something else. But spin is unique. Spin is absolute. You can feel it without looking outside. You know when you are dizzy. You know when you are turning. This suggests that deep inside, we have an internal compass. We have a sense of orientation. And just as the electron aligns itself with the magnetic field to find its lowest energy state, to find its peace, we too are constantly trying to align ourselves. We are trying to align with our values, with our loved ones, with the truth of our lives. When we are misaligned, we feel the torque, we feel the wobble, we feel the energy cost of fighting the field. But when we align, when we find our resonance, we feel the snap of connection. We feel the resistance fade. We enter a state of flow. We become like the superconductor, letting the current of life pass through us without friction. The journey of the electron is the journey of finding that alignment. It is the story of a tiny spark of existence looking for its place in the great magnetic web of the cosmos. And it finds it. It always finds it. The electron never gets lost. It always knows exactly how to spin, exactly how to exclude, exactly how to bond. It obeys the laws of the universe with a perfect, effortless obedience. We can learn from this. We can trust that we, too, belong here. We are made of the same material. We are subject to the same laws. The gravity that holds the moon holds you. The exclusion principle that gives the diamond its hardness gives you your form. You are not a stranger in the universe. You are a child of the spin. As we close this book of exploration, I want you to visualize the layers we have uncovered, stacking them one on top of the other like sheets of glass. See the bottom layer, the string, the tiny vibrating loop of 10-dimensional energy singing the note of existence. See the next layer, the particle, the point-like electron flashing in and out of the vacuum, wrapped in its cloud of virtual photons. See the next layer, the atom, the heavy nucleus surrounded by the shell of electrons, organized by the strict rules of the Pauli exclusion principle. See the next layer, the magnet, the armies of iron atoms aligning their spins to create a force that can guide a ship. See the next layer, the life, the complex molecules of DNA and protein held together by the exchange of photons, folding and twisting to create the machinery of you. See the next layer, the mind, the neural currents and magnetic fields of your brain, processing the information of the cosmos. And finally, see the top layer, the awareness, the quiet, observing presence that holds it all together. It is a masterpiece of construction. It is a tower of trembling, spinning miracles. And it is all happening right now, in the dark, without you having to do a single thing. You do not have to tell your electrons to spin. You do not have to tell your atoms to hold together. The universe carries you. So let go. Let go of the need to control. Let go of the need to be rigid. Embrace the spin. Feel the gentle rotation of the Earth carrying you eastward into the morning. Feel the solar system carrying you around the galactic core. Feel the galaxy drifting through the cosmic web. You are a passenger on a magnificent voyage that has no destination, only a continuous, beautiful unfolding. The mystery of why the electron spins may never be fully solved, and perhaps one day we will find a theory that replaces strings or explains the paradox in a way we cannot yet conceive. Science is a river, not a pond. It keeps moving, but the wonder of the discovery will remain. The feeling of awe that we felt when we first looked at the black hole, or when we first imagined the quantum computer, that is the true prize. Knowledge is not just about power. Knowledge is about intimacy. The more we know about the universe, the closer we feel to it. When you know that the starlight hitting your eye is a stream of bosons, and that your eye is a lattice of fermions, the act of looking at the star becomes a handshake between the two families of creation. You are no longer just looking at the sky. You are touching it. I hope this journey has brought you a sense of peace. I hope it has replaced the anxiety of the unknown with the comfort of the magnificent. We live in a reality that is far stranger, far more complex, and far more beautiful than our ancestors could have ever dreamed. And you are a part of it. You are not small. You are significant. You are the universe becoming aware of its own spin. As you drift off into sleep, let the image of the spinning electron be a lullaby. Let it remind you that movement is natural, that cycles are safe, and that even in the deepest darkness, there is always, always a rhythm. The dance never stops. The music never ends. And you, my friend, are one of the dancers. Thank you for walking this path with me. Thank you for lending me your imagination and your curiosity. There are infinite stories left to tell, infinite mysteries left to unravel. The cosmos is vast, and our journey has only just begun. But for now, the screen fades to black. The voice falls silent. The physics book is closed. Sleep well in the spinning arms of the night.